Alright, hello. Let's see. Alright, first off, I want to show you, like last time, we did a bunch of quad tree changes, and yeah, there was some weird stuff happening with the physics, and I went ahead and fixed those issues. So the problem was that in our intersect function, or okay, I made a bunch of refactorings as well. So basically, the physics step is divided into 8 sub-steps. So each frame, there's 8 physics updates. And this just to get the collision precision, a better collision precision basically. And the better precision you have, the more, I guess, realistic the collisions will be. But 8 is kind of a good number to have for this project here. And I had an idea that if I build a quad tree, the first sub-step and then the subsequent 7 sub-steps, I will use the existing quad tree to calculate, to check, like we don't have to build a tree again, the subsequent sub-steps, because the changes in the positions should be very small, so there should probably be almost no entities that need to sort of change their parent in the quad tree. But I did write an update positions function that will go ahead and check all the entities, and if they have updated their position to be not contained anymore, they need to be reinserted basically. Well, I'm not really reinserting it, I'm doing like a fast reinsert to just put it in a parent that is the first available parent basically. And then we do the search and reporting sections as normal. So the problem that was that I never actually updated the positions. So I basically just took the cached positions and used them every time. And that's why the collisions looked a bit weird. But now we're fetching the updated position again, and then we're updating the cache from it as well, so in the quad tree. So that fixed the problem, and overall we saved some frames. You could say that's like a speedrun term, but I just realized, but well, we didn't save frames. That means we have lower frames or less frames. We have more, we can put more frames into each second basically. So but yeah, so that is the update. So now if we let's see if I can run the demo now. I want to run optimize release fast. No, not npm. Zig. No. I'm so that's like an npm thing, like you say npm run. Okay, so here you can see all the little all these little physics bodies here, and I can move this guy. So now it's way more accurate, but there's still some issues. I think it's I don't really know if it's because the bodies are so small or something. I have no idea. But sometimes they get like stuck and they just vibrate a little bit. I don't really know what's going on there. Maybe they like take up each other's since I think they are like one by one. or maybe 2 by 2 or something. So it's easy for them to maybe get like completely contained, like two of the rectangles get, or squares get completely, you know, have the same position. And if that happens, I don't really know. I don't think it's like super stable. Also, I enable them to collide with each other, as you can see here. And if we enable the quad tree, you can see that the quad tree visualization, all those little black rectangles are the deepest quadrants. But even if we are in this, if you can look at the big square here, and we're going to the edge here, we don't get another subdivision here because we are the only body in this quadrant here. Now we could actually play around here and say we could increase the number of entities that's needed for subdivision. That will actually change the quad tree a lot. Let's look at how many bodies we have. 5,200, or I mean 5,002. Let's actually, I just want to, I'm not gonna play around with this too much here. I'm just curious if we increase this to maybe, I don't know, 10. Because then there's gonna be up to 10 entries in one quadrant, or one node, which will lower the depth of the overall tree. But it will increase, I guess, once you find the quadrant, I guess it will increase the number of checks there. Okay, so you can see there's way less black quadrants now. We actually do get more bodies at this point. We get 100 more bodies, and that's because this is faster. So that actually made it faster. So we could tweak. You can tweak the parameter like that. Yeah. Okay. Well, that's what I wanted to show there, and that also solved an issue in the actual game that made the player sort of yeah, the collisions didn't work properly. So, but I'm actually gonna go ahead and do this. Will this put it in ziglings? I've never done this, so I think it's time. I've been developing in Zig now for like a year or something, and I've never done this tutorial thing. Because yeah, I think maybe this will help me cover some of the bases. You know, I should probably do this since I want to learn more about the language. Yeah, so so how do we do this? Let's read the README. Ziglings. Welcome to Ziglings. This project contains a series of tiny broken programs and one NASA surprise. Oh, okay, yeah. And I did check, this uses the latest Zig version, so actually we need to use like master. Actually, maybe I should use 0.15 for this. I'm gonna check here. Can we get that tag instead? I'm gonna go to this, or maybe, I mean, yeah, this is Codeberg. I'm not familiar with that. Packages, projects. One second here. Codeberg. Is this like I don't know what this is. tags. There we go. Oh, here we go. Okay. I don't remember how you clone, how you choose tags. Let's do this. Remove this. And then we clone. Can you clone? Can you grab tag? Can you do this? Maybe? No? Okay, 1 second. Bronze? No. Okay, so let's do bronze. I'm not sure if this matters, but we'll do bronze. And then into this. No. Okay. Let's try this. No? How do I clone this? Okay, well there was a commit. Yeah. Git clone commit. Git reset. Okay. Okay, so we'll do this. Go in here and then now this should be. Oh. Okay, well, I guess that's fine. It does say the tag says 0.15.1. So, all right. Yeah. Okay, let's yeah. Okay, let's just do this. This should be fine. All right. Welcome to ziglings project. This project contains a series of tiny broken programs and one nasty surprise. By fixing them, you'll learn how to read and write Zig code. Yes, thank you. Those broken programs need your help. You also save the planet from evil aliens and help some friendly elephants stick together, which is very sweet of you. Well, yes. This project was initiated by Dave Gower and is directly inspired by the brilliant and fun Rustlings project. Okay. I might actually try that because I'm very interested in just doing the learning part, like just doing the because I'm very like I probably know most of the features, but what I don't know about is the borrow checker and, you know, all the things that comes out of that. Well, anyway, indirect inspiration comes from Ruby cones and the little Lisper little skill. Okay. This would probably be difficult if you've never programmed before, but no specific programming experience is required, and in particular you are not expected to have any prior experience with systems programming or a systems level language such as C. Okay. Each exercise is self-contained and self-explained, however you're encouraged to also check out these SIG language resources for more detail. Yes. Zig in depth. I think I started on that, but I never sort of watched everything because it's so long, and it's a very good series. I think if it's the one that I'm thinking of, and if it's the one that I'm thinking of, let me just double check this. Well, I can't. Dude, by Dude the Builder. Yeah, this is the one. Yeah, very good series. Highly recommend that if you want to very deep dive into Zig and learn a lot. Really nice. Yeah, goes into basically everything. Yeah. You know, you have to have a bit of patience. The videos are kind of long. I was basically using them as a way to sort of look up certain things, because there's not much resources out there that has that you know, stack. There's basically no Stack Overflow questions with Zig, so you have to look at documentation, random posts and videos and stuff. So, but that's part of the fun. Okay, also Zig community is incredibly. I never been there, but I guess, yeah, I'll check it out sometime. Getting started, install. I have checked out Zig on Discord, which is very active, and a good place where you can ask questions in a channel there, and or one of those posts. You make a post and explain your question, and someone will come and help you. Very cool community there. Install a development build, and there's a bunch of other things in there as well. Discussions about all and everything. Install a development build of the C compiler. See the must section. Well, I have. This should probably be compatible because I'm running 0.15.1, and this should be 0.15.1. Yes, I've done this, and then we can run Zig build. Okay, so let's try this Zig build just to see there's no weird errors. Okay, here we go. So this is supposed to happen, I guess. Let's make this a bit larger. So let's see, we're greeted with this. I think they maybe put this in the build step. I'm not sure. I don't remember how, if that was possible. Because the build command, basically it compiles the build.zig file and sets up some build steps, and then when you say Zig build, it will build the default one, or it will build everything you've marked as this should be built or something. But I'm not sure how to actually get this output here. But anyway, that would be interesting to see. Not that I'm gonna use it myself, but it's just interesting. Okay, so we're compiling the first program here, following command. Failed with one compilation errors. Main is not marked pub. Seems to be easy to fix. Okay, let's go to one. What's this patch here? Okay, so they have like the answers here, I guess. Yeah. Okay. Well. Oh no, this is supposed to print hello world, but it needs your help. Zig functions are private by default, but the main function should be public. A function is made public with the pub statement like so. Yes, I'm very aware of this. Yeah, the first one's gonna be super easy. Okay, so I guess we'll run this again. And great, we passed the first one. So now we're on to the second one. This is a really fun way to do things. Alright, so let's do... I mean, it reminds me of the advent of code type thing. Oh, that would be cool to do in Zig, actually. Man, that would be... I don't know. Advent of code is like, I usually want to use like a very easy language just so I don't have to worry about all the things, you know, garbage collection or something. Yeah, but or just, you know, an easy way of doing things. Like, it's not like Zig is... sometimes it's super easy to do some things, and sometimes it's very hard, like especially with the memory management. That's probably the part that's most annoying. But I love it anyway. Oops, this program is supposed to print a line like our hello world example, but we forgot to how to import the Zig standard library. The import function is built into Zig. It returns a value which represents the imported code. It's a good idea to store the import as a constant value with the same name as the import. Const foo equals import foo. Yeah, it's, you know, this is things you learn over time, like how you want to do things. Yeah, this needs to be const standard or stud equals import at import stud. And you can also, like, this is equivalent to this now, so you can say like stud dot, and then you get all these standard libraries things, but you can also do it here. So if you, for example, just want the allocator, now I usually say, you know, this first. There's even a snippet here, and then say allocator equals men allocator. You can also just say this instead. It's like equivalent. It's just an alias basically. But you can also say, if you only want the allocator, for example, you can also say this. I never do this because I usually need more things maybe, but just to show that it's possible and kind of get an idea of what's happening here. Yeah, anyway, so this should be fine. Okay, and then we're printing out standard library there. Okay. Now we're using this standard debug print, which is sort of the easy way of printing stuff. It's pretty funny because Zig now has, like, if you want to print to standard out, because this one does print to standard out, but since we're using like, well, actually this is debug print. I was thinking of log debug. Yeah, this is another way to do it, but this will prefix the this would like prefix debug colon space, but it's basically the same thing. This one, I guess, will just print it out. So this is like an easy way to print things, but it's not, I guess, the correct way you should use like in production. since it's like the debug. I don't know really the difference. This just uses, I mean, basically, okay, it's using weird things I've never seen here. No suspend. I don't actually know what that is. Interesting. But what I wanted to say is that if you want to print this using sort of, I guess, the standard way of doing it, you don't do it like this. But maybe we'll get to that here. For the curious, imports must be declared as constants because they can only be used as at compile time rather than runtime. Zig evaluates constant values at compile time. Yes, don't worry, we'll cover imports in detail. Yeah, so there's like compile time. Of course, every language has this, like, things happen in compile time. Like you have constants. If you have a constant, x equals 5, you know, x, this is a constant. So whenever you use x, you're not actually, you know, taking up memory in or anything like that. They just replace x with 5. And also, if you do like x 5 times 25, this will actually get evaluated in compile time and not in, you know, in runtime. So it doesn't cost anything. I mean, I guess it costs compile time, but that's not really a huge deal. Okay. Also see this answer. Okay, sure. Yeah, whoops. Oh, it opened in the Linux version or WSL version. Let's see. That compiles because, wait. Yeah, I don't think you can have a var, because the thing is, this is a type. This is a type. So you're basically defining a type. This is a type definition. And you cannot modify it, because what will happen then? Like, how would like if you modify it later, you cannot accept the same type. The types has to be constant. Because you know, if you have a function that receives a variable of this type, which version of the type are you gonna use? Yeah, so I mean, yeah. Okay, interesting. Okay, let's run and on to the next one. Cannot assign to a constant. Yes, usually in programming you cannot do that. Whoops. Here we go. It seems we got a little carried away making everything const. U8, okay. And U8, of course, means that's a type, and it means U means unsigned. You have signed and unsigned integers, where signed means that you can have negative and positive numbers. Unsigned means you have only positive numbers, and the reason for that is because if you have unsigned, you can have larger numbers. You free up the information that says if it's negative or not. It's basically, if you think about math, if you take a U8, that's, so the 8 means 8 bits, and 8 bits means 2 to the power of 8 combinations, which is 256. So, excuse me. Sneeze there, excuse me. So if you have a U8, that means you have from 0 to 255, because you have 256 combinations, and the first one is 0. So you go from 0 to 255, that's 256 unique combinations. And if you have a signed number, one of the bits will toggle. So a bit can be 1 or 0. And so then you will have to use one bit to toggle if it's negative or positive. Which means that now you don't have 2 to the power of 8 combinations anymore, you have 2 to the power of 7. I mean, okay, you still have 2 to the power of 8 combinations, but the value can go up to, yeah, here it says 127. So you have like, or negative 128, and that's 256 different combinations. And if const means that it's a constant, which means it can't change. And the opposite of that is a var, which means variable. So it can be changed. It's also called mutable oftentimes in programming. We have immutable, which is cannot change, and that's the same as const. And you have mutable, which is in this case same as variable here. But it's also a bit confusing because usually you always say variable when you're talking about something, some kind of name, which is this, which we call an identifier. So foo is an identifier of the constant here, and the type is U8 and the value is 20. So you have, you know, is it mutable or immutable? Is it constant or variable? The identifier, the type, and the value. I don't know why I'm going through this here. Very, I mean, I guess since they are talking about it like very, this is very like basic stuff, I guess. I mean, if you're a programmer, you should probably know most of this stuff. It depends on what your background is. Like if you're coming from a dynamically typed language, you don't know too much about these types because you're just, it's a number or it's a string or something. But here we have different types of numbers, which determines how much, you know, 8 bits takes up 8 bits in memory. So it takes up different, you can have U16, U32, which takes up different amounts of memory. And maybe, you know, I don't know, I don't remember if Python actually has like constants. Maybe it does, but I think JavaScript for a very long time did not have constants. So you couldn't define anything like, you could only have mutable variables that you could change. So that concept could, but you know, variables like should be a concept that is familiar to you if you know any kind of programming language. Let's see here. Foo cannot be negative and hold 0 to 55. Yes. Yeah, so they're talking about the difference between unsigned and signed integers, which we talked about here. And now here we're talking about, okay, if you have a U16, you can hold a value up to 65,535, which is 2 to the power of 16. So you can see here, you can calculate how large the integer is by calculating 2 to the power of x, where x is the number of bits. So U32 will have, well, you can see here, this is 2 to the power of 32. And also 2 to the power of x means that every time you increase x, you double the number. So if we take an example here, like 8 bits, if you increase that to 9, that will become, so 8 bits is 256, 9 will become the double of that, which is 512. And 16 is 2 doubled 16 times, which is 65,536. and it increases very rapidly here. So here U32 is like 4 billion, 4.3 billion, and then 64-bit is insane. So basically nowadays we have 64-bit based systems, and if you have a 64-bit number, you basically don't need more than that for most things, unless you're dealing with like super precision simulations or something. But or maybe one of those incremental idle games go up very high in number as well. I'm not sure how they do it. If they just increase the number of bits or something. But yeah. Anyway, let's see what's going on here. So with the knowledge that we have now, we know about constants, mutable variables. We have a constant n u8 equals 50, and we're trying to reassign, which we're doing here. So we're saying that n should now be equal to n plus 5. But since n is immutable or a constant, we can't do that. So we have to change this into a variable. Now in this contrived example, you would probably just say instead that this should be 55, or just 50 plus 5 if you want to keep the sort of intention here. But yeah, I think they want us to make this into a var, which will probably solve the issue. What are we doing here? We're defining pi as a u8. Okay, this is wrong on a couple of levels here, so let's make this into, I don't know if they told us about floating point numbers. So can we use floating point? Okay, this doesn't work. I mean, this is weird. They're saying this is pi. We haven't learned about floating point. We need floating point to define pi, but fine. This could be, this is 314,000 here. So we need U32. You can actually use like U18, U20. You can actually define any integer here. The reason why we're using mostly like U8, U16, U32 is for both for like historical reasons, but also the computer architecture, memory, and how the hardware works like they kind of assume that there's some that things come in yeah, it's what they call alignment. I'm having a hard time formulating this, but basically everything, memory and everything, is aligned at like 64. In a 64-bit system, it's aligned at 64 bits. So it's easier for the computer to deal with numbers or deal with data that is like, that has that size. But you can use U20 or whatever here if you want. Now this one is negative, so we need to change this from an unsigned to a signed integer, which you, instead of, you don't say S8 for signed, you say I, which stands for integer, I'm pretty sure. But yeah. What's this? There are no errors in the next line, just explanation. Perhaps you noticed before that the print function takes 2 parameters. Now it will make more sense. The first parameter is a string. The string may contain placeholders, which is the curly brackets or braces, or what's it called. And the second parameter is an anonymous list literal. Yeah. Don't worry about this for now, with the values to be printed. So anonymous list literal. It's basically just, in other languages, this will be called like a tuple with variable length. You can put whatever values in here as you like. Like, it doesn't have to be the same type. It's not an array in that sense. It's actually a struct with the names. So it is a struct, and the names of the fields here. There's one field created for each of these elements, and the name of them is like 0, 1, and 2. And then you can use comtime to loop through those values and print them. And here, this string here is used to put these in the correct order. So the first one, second one, third one. So the first one is the first one in the tuple, which is n. This is pi, and this is -11. And then we have an end line marker here. Okay, so let's see if this works. Yes, so 3 is passed, and now we're on to 4 arrays. So we're moving fast. I mean, you're not gonna learn programming from this. It's basically aimed towards people who have some kind of programming background, but they want to learn Zig as a new language. Okay, let's learn some array basics. Arrays are declared with this. So we have the variable, so it's mutable. The identifier is foo. We have the type, which in this case is an array. So with 3 elements. And this is a basic, you know, it's the same as like a C array in C or C++. And yeah, it's just a list of, it's just, you know, a list of numbers. The interesting thing with arrays is I usually don't use these. But we'll get to that later, because there's another construct that you might want to use instead. When Sig can infer the size of the array, you can use underscore for the size. Yes, you can also let Sig infer the type of the values. The declaration is much less verbose. Yeah, so you don't have to put the number here. If you know how many, if we specify these numbers, Zig will figure out that it's 3, so we don't have to spell it out. And also we put the type here. This is like when you sort of construct something that is like a struct or an array like this, you put the type here first, and then you put curly braces and then the content within here. So that's how you sort of declare a value of this type. And yeah, and here we can infer the number. And the type now doesn't have to be specified for this assignment or declaration here, because it can be inferred by the value, by the assigned type. Okay, get values of an array using array index notation. Yeah, so basically just accessing element n in the array, and yeah, the end. So element 2 means actually this one, because you start at 0. So this one is 0, this one is 1 and 2. Okay, set values of an array using array index. Yeah, so basically here we're just assigning the element number 2 to 60. Get the length of an array using a length property. Right, so all arrays have a len property that you can use. It's interesting that they call it property, because usually it's called a field. But that's also like, you know, in programming lingo, that's basically the same thing, except in C#, I don't know if maybe Java as well, they have a separate notion of properties and fields, but you know, it's basically the same thing. It's just something you can access on this, which is not a function. It's, well, Yeah, it's something you can access on the array to get the length of the array. It's basically saying I want the length of this array here, which is 3 in this case. All right, so what's the issue here? Problem 1. This const is going to cause problems later. Can you see what it is? How do we fix it? So there's no problem on this line itself. We're just defining a bunch of primes here with U8 as type, and the array has some things. However, here we can see on the next one, individuals values can be set with brackets notation, square brackets. This line changes the first prime to 2, which is correct. And yes, but since this is a const, it's immutable, means that you cannot change anything in this array. So we have to change this into a var, and now it's mutable. Okay, so that was problem 1. Next up, individual values can also be accessed with the square brackets notation. Example, this line stores the first prime in first. Yes, so basically what's happening here is we're making a constant that copies the value in this array. So it's not a reference or anything. It's a copy into first. And here we have problem 2. Looks like we need to complete this expression. Use the example above to set fourth to the fourth element of the sum primes array. So the fourth element means number 3 because we start at 0. The first element is 0, second is 2, and so on. Problem 3, use the length property to get the length of the array. Okay, so there you go. And we're printing it out here. Okay, that should be done. Now we're on to arrays 2. Zig is some fun array operators. You can use plus plus to concatenate 2 arrays. Yes, an important part of this is that this is kind of truth with some modification. They left out, I mean, they're probably gonna say it later, but this only works for compile time arrays, compile time known arrays. So these constant arrays can be concatenated with plus plus, but that's not true for all arrays. You cannot do this with mutable arrays or runtime known arrays, or arrays that are not known in compile time. Okay, but here they showing how to concatenate. So we have an array A with 1, 2, array B with 3, 4. If we concatenate that, this should be an array, a new array with 1, 2, 3, 4, and then we're concatenating this with another array which only has 5. So C will become 1, 2, 3, 4, 5. Okay, and this one is also very interesting. I've never seen this before. In another program language, maybe it does exist, I don't know, but you're basically repeating the entire array X amount of times, and I've not used this a whole bunch, but it has seen some use, so it's an interesting feature, and I guess it's good to have sometimes. But it is not used often, but yeah, you can repeat stuff with that, which is nice. So you repeat the whole array. So this will become 1, 2, 3, 1, 2, 3. All right. Note that both plus plus and asterisk only, or star or whatever, only operate on arrays while your program is being compiled. Yes, it has to be comp time known. This special time is known in Zig parlance as comp time, and we'll learn plenty more about that later. Yes. Yeah. Again, you can't do that on runtime known only stuff. Okay, so this will be this, because Li is 1 3, eat is 3 7. Problem 2, please set this array using repetition. It should result in 1 0 0 1 1 0 0 1 1 0 0. So we need a 1 0 0 1 repetition 3 times. That should be good. Okay, that's all the problems. Let's see the result. We could print this arrays with lead 0, lead 1, but let's have a little preview of Zig for loops instead. Whoa. For item array, item, do something with item. Don't worry, we'll cover looping properly now. Yes. So we're printing out lead. So this just prints out the string lead, and then we're looping through lead with this loop here, and this is called a capture. So we're capturing each element in this capture thing. So n, we're assigning the identifier n to whatever element we are currently on, and it will go from 0 to the end of elements, or the first element to the end. Yeah, and then we're using that there, and here we have bits. Oh yeah, that was the second problem. Okay, so let's do this. There we go, that works. Okay, let's go on to the next one. Strings. Now that we learned about arrays, we can talk about strings. We're moving very fast here. I mean, if you're actually learning programming for the first time, I don't think it's gonna stick by just doing this. I mean, it's nice they go through a lot of the concepts very simple, and I do like, because this is one of the languages which could be pretty easy to get started with. However, when you get to some of the manual memory management, that's gonna be hard. But you know, since you don't have to worry about classes or anything like that, the only thing you have is the main function, but we haven't even touched on functions yet. But if you're totally new, this could be a good introduction language. But you know, it's gonna get hard later. But anyway. Now that we learned about arrays, we will talk about strings. We've already seen Zig strings literals. Yes. Zig stores strings as arrays of bytes. Yes. It's almost the same as this. I mean, yeah. So the difference is that this is like comp time, a comp time known string. So this is kind of like I don't know if it's called like polymorphic, but it's like it can take on different types depending on where you use it, because there are different types of arrays, like U8 arrays, like this is a byte array, but you can have different flavors of that. And here we're basically saying that it should be this flavor, like it should be an array of U8s, but this one can be like used in different you know, you can pass it to different things which requires different flavors, and it will still work. But this one you actually have to use this specific type to use it. So I think that's what they mean here. Maybe there's something else that I don't know about, but yeah. We'll see what Zig strings really are in exercise 77. Holy shit, how many exercises are there here? Notice how individual characters use single quotes H, and strings use double quotes. Yeah, so there's a difference. So this is actually not a string. It's just one. It's the same as a number, but it's like the ASCII. Yeah, it's one character in a string. So double quotes, you can have several characters. Single quotes, you only have one. You have exactly one. Okay. Problem 1. Use array square bracket syntax to get the letter D from the string stardust above. Okay. So first is 0, 1, 2, 3, 4. So this should be 4. Okay. Use the array to repeat to make ha ha ha. Okay, we just repeat 3. And use the array concatenation operator to make Major Tom. Aha, but you need to add a space as well. So we can do plus plus space plus plus Tom. And that will concatenate that. And remember, you can only do this in comp time, so they're kind of showing you you know, it's kind of cheating here a little bit, since this is only for comp time known arrays. You cannot do this with runtime known only arrays. You have to use allocators and concatenation function from well, you can do it manually if you want, or you can use the standard library concatenate function. But I guess they will come to that. That's all the problems. Let's see our results. Yeah, so here we're not using just square or curly braces, we're actually saying something in here as well. So U means what? Something. So basically you're determining the format of the thing you want to print. S means you have to put S to say that this should be a string. And you have to put S every time you're trying to print an array. You have to put something in here like S or I think D if you want to use like a number or something like that. But what is U? Format the values as a UTF-8 character. UTF-8 strings separately. Oh, I see. So this is a character. I see. So if you only have one character you want to print. Ah, I didn't actually know that. Okay. While we're working on the subject, C, ASCII encoded character would work in place of for U because the first 128 characters of UTF-8 are the same as ASCII. What? C would work in place for U. Oh, I see. Okay, or they're talking about this, the format. So if you put C here, it means the ASCII format, but U means the UTF-8. Okay. Yeah. I'm not gonna go into UTF-8 versus ASCII, but basically, there's to say here, the first 128 characters are the same. So, yeah. Okay, what's going on here? Okay, yeah, now we're on the next one. So 7. Here's a fun one. Zig has multi-line strings. Man, I don't like these. To be honest, to make a multi-line string, put slash backslash at the beginning of each line, just like a code comment, but with backslashes instead. Const 2 lines, and yes, see if you can make this program print some song lyrics. Well, I mean, there you go. I never use those. It's like I don't know. Yeah. It's kind of weird. Like it's kind of different if you compare this to other languages, because I think most other language has some kind of marker to where it starts and ends. But basically the Zig ones, they take up this whole line, so you can't have, you know, some kind of end here you have to. This whole line is taken by the multi-line thing, and I guess it kind of ends here, because here's the first one that you don't have a backslash backslash, and here's the first one that you do have. So they have to have their own lines, and they have to be they take out the whole line. But in other languages you might have something like this. You have like something like that instead, and then the actual content is not polluted by some weird backslashes. But yeah, I don't know. There's like pros and cons with both approaches, but I basically never use those. Well, very seldom use those. Okay, next one is the quiz. Quiz time. Let's see if you can fix this whole program. You have to think about this for a bit. Let the compiler tell we was wrong. Start at the top. Okay, now we need to think here. What is this nonsense? I don't know. Letters equals wise. usize is an unsigned integer type used for sizes. Yeah, this is a kind of weird thing. It's like, yeah, it depends. So usize is basically, it's either U32 or U64. I mean, it could be, it depends. It says here, it depends on the CPU architecture. So whatever architecture you're compiling against, if you're compiling against a 32-bit system, it's going to be 32, a U32. If you're compiling a 64, it's going to be U64. But it is used for loops. So if I have a loop here, I here, the type of I is a usize. So you have to keep this in mind. If you're gonna use I to compare or do anything with something that is like a U32, then let's say we have another variable which is I plus y plus I. Whoops. Then yeah, you have to think about sort of the conversion and everything in here when you do this. So I, like, for loops always produce an I. So usize is like the index type, like for using for index in arrays and slices and everything. So it's a very important type. You're gonna use it a lot, but you have to know about it. Well, you're gonna know about it because it's gonna be a whole bunch of errors if you try to use like U32 or U64. But yeah, it's not bad. It's just that it's, you know, a little bit different there. Okay, so let's see. Note when you wait. So what is there's a problem. Well, if it's not usize, it's either if it needs to be constant, or I mean variable, or maybe the identifier is wrong. Not the type, okay, maybe the value, I don't know. Let's yeah, okay, we can see here that we are reassigning x, so we need to make this into a mutable. Okay, next one. Note, when you want to declare memory or an array in this case without putting anything in it, you can set it to undefined. There is no problem on this line. Okay, if you say so. Varlang 3 U8, yes. So this is also a new thing. So undefined means that you're declaring the variable, but you're not setting it to any value, which is sort of the standard thing that happens. I mean, I guess the thing that actually happens here is that the compiler will make room for this variable, but it's not actually going to do anything with the value, which means that the room that it took up could, I mean, it already has some value in it. So the initial value of this is unknown. It's undefined. Well, yeah, it's not known in compile time. I guess you can say. It's gonna be totally random based on whatever garbage was in the memory spot that this memory or array was defined in. So that's what undefined means. And if you remove this, that's gonna be an error because you always have to set the variables to something. So you have to put equals undefined, which I think is a good thing because you're kind of, it's a bit more strong feeling of, okay, I'm actually setting this to undefined and this is purposefully set to undefined. Right. So that, I think that's a really good language feature. The following lines attempt to put Z, I, and G into the lang array, which is created by indexing the array letters and the variable x. As you can see above, x equals 1. To begin with, lang 0 equals letters x. Wait, the following lines attempt to put capital X, capital Z, I, G into the lang array, which is created by indexing the array letters with the variable x, as long as you can see above, x equals 1 to begin with. Okay. Yes. So we need Z, which is this number 1, which is correct. Then we're setting this to 3, and supposedly we put this in 1. X is 3, which means I, and then G is 5. And we still need to use X here. Now this is a very not how you would do it in actual programming, but it is for learning. So that's usually that's kind of one problem I have also with the learning things. It's like, you can do this, but I mean, yes, it's good for learning maybe, but it's not how you would actually do it later. So you're not actually learning. It would be cool if they added an example, like in real life you wouldn't use this, you wouldn't say it like this, you would, this is only for demonstration purposes, but you would say something like this, and then you know, you wouldn't use X at all, probably. Okay, well, anyway, we want to program in Zig, of course. I see, that's what we spelled. Okay, I actually missed that. Yes, program in Zig, of course. Interesting, they spell it with the capital Z. I thought that they usually said like lowercase z. I'm interchanging Z and Z because I have no preference. Okay, so now we're on exercise number 9. If. Now we get into the fun stuff. Starting with the if statement. If true, else yes. Zig has the usual comparison operators such as equals, lower than, greater than, not equals. The important thing about Zig is if that it only accepts Boolean values. It won't coerce numbers or other types of data to true or false, which is a very nice thing. Very, very nice thing, because it reduces the amount of confusion that you might have. So foo equals 1, that is true, because that's what it is. Foo is set to 1. So here we're saying foo is 1, so we have to add this to make it into a Boolean, and here is not 1. Great, very simple. Okay, if statements are also valid expressions, const foo u8 if a 2 else 3. Yes. So yeah, this is kind of like, this is like exactly like a ternary expression in C or C++ or other languages like that. except that the syntax is different. So it's an expression that gets evaluated and the result is put into this variable. So it's the same thing as saying in other language, like A, 2, 3, but it has like if-else syntax instead. Please use an if-else expression to set the price. So if discount price is 17, otherwise, oops, else 20. Okay. It's fun when they introduce things like this. It feels like you're almost programming something like some kind of business logic here. When you're talking about, it's so interesting how much the theme of these variables change the feeling of what you're actually programming. So now we're making a business logic here of the price, recalculating the price. Okay. Yes. And 11. While. Sig while statements create a loop that runs while condition is true. This runs once at most while condition is equal false. And then the next loop, the next iteration, condition will be false, so it won't run anymore. It will go down here. Remember that the condition must be a Boolean value and that we can get a Boolean value from conditional operators such as, yes, so it's the same thing. Okay. So n, mutable n, u32 equals 2. Please use a condition that is true until n reaches 1024. Okay. Oops. So n is less than 1024. So this is true until n is 1024. Or more. So we're printing it out, multiplying it by 2. So how many iterations would this be? We start at 2. That's 2 to the power of 1. 1024 is 2 to the power of 10. And so we start at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's so easy to get a one-off error when you're counting iterations and stuff. Start at 1. So 1 iteration. So I guess is it gonna be 10 iterations? 1, 2, 3, 4, 5, 6, 7, 8, 9. No, it's gonna be 9 iterations, I think. So it's gonna print 2, 4, 8, blah 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 up to 512, and then n equals 1024. I think. Oops, I never saved. Yes. Okay. That's also like an exercise I usually do. Like I had to do a lot in the beginning. Is for loops especially. It's like, okay, what's gonna happen the first loop? And sometimes I do this nowadays also to just go through each iteration to see, okay, first is this, then is this, then so yeah, it's a bit nostalgic actually. Okay, 0, 12 while 2. Zig while statements have an optional continue expression which runs every time the while loop continues, either at the end of the loop or when explicit continue is invoked. We'll try out those next. While condition, continue expression. Okay, wow. I've actually never seen this or used this. This is totally new to me. Holy moly. Example, var equals 2 while foo is less than 10. Continue expression, foo plus equals 2. Oh, so it's like the either at the end. Oh, it's ran every time the while loop continues, at the end of the loop or when a continue is invoked. So it's like the old, like, you know, in other languages you have like the for loop. I mean, okay, let's take C here. For, so you have like int I equals 0. But you don't need to say that. You have I equals 0. So that's the, like the start. I less than 10, that's the condition, and I plus equals 2. I guess this will be set to 2 if it's gonna be equivalent here. So this would be an equivalent of this. Okay, I've never seen that. Wow. I mean, I don't use it that often, like this type of thing, but that's very cool. See, going through these basic things cover the basis of the language, so that's cool. All right, so let's see if we can rewrite the last exercise using a continue expression. Okay. Well, now it's just 1,000. I guess that's the same thing, you know, logically. We double it. Yeah. So, yeah. So this is run whenever the while loop ends. Or, I mean, it's whenever the iteration ends. Yeah. Okay, cool. We're at 12, so let's go to 13. Last two exercises were functionally identical. Continue expressions really show their utility when used with continue statements. Okay. Yeah, so if you have a, if you have a continue, the continue expression will run there as well. You could, I mean, I wonder if you can have like, I mean, I guess you could have like a side effect. I mean, it is a side effect modifying the variable, but like calling a function or something in the continue expression. The continue expression executes every time the loop restarts, whether the continue statement happens or not. So, wait, the continue expression executes every time the loop restarts, whether the continue statement happens or not. Yes. I want to print every number between 1 and 20 that is not divisible by 3 or 5. Okay. The percent symbol is the modulo operator, yes, and it returns the remainder after division. Yeah. People who know the maths here would be familiar with the modulo operator, although its math is not used. You don't use a percentage. I wonder where that came from, actually. But this is like n modulo 3. And okay, which basically means if n modulo 3 is 0, it means that multiples of 3, this is n, this expression will be 0 in multiples whenever n is a multiple of 3, and here's n is a multiple of 5. So if the remainder is 0, then that means that it's a multiple of 3 or 5 here. So what do you want? Do you want to print every number between 1 and 20? I guess, yeah, I think their idea is that if this happens, we should skip this iteration, so we should continue here and here, because now we're only printing those that are not continued. And yes, that works. Okay, on to the next one. While for, you can force a loop to exit immediately with a break statement. While condition, continue expression, other condition, break. Yes, which will exit the loop. Continue expressions do not execute while when a while loop stops because of a break. Yeah, okay. Oh dear, this while loop will go on forever, while true. Please fix this so the print statements below gives the desired input. Now this is basically going to be equivalent to putting the expression that's in here instead. So it's kind of a weird example, but we want n equals 4. So if n is if n is equal 4, then we break. And that should solve the issue. So it should loop first n is 1. It checks if n is equal to 4, that's false, so it goes on here, we exit or we continue, so we should run this. So now n is 2, next iteration n is 2, and so on until n is 4, which then we break and we don't run this, crucially. So now n is 4 down here. Yes. Alright, 15. Behold the for loop. For loops let you execute code for each element of an array. 4 items. So it's basically like a while loop, except it always has like an ending, like a finite number of iterations, you could say. I guess except when it doesn't. I mean, it's just a convenient way to say, hey, I want to loop through all of the items in an array. That's basically what this version of for is. But you can, I guess they're gonna go through that as well. But anyway, 4 items, item do something with item. Yes, and here we are looping through all the. So this is an array, or some kind of iterable thing, and we're capturing the element here with item. All right, that's what it's called. It's called a capture. Okay, we have a story apparently. HHSNH, a dramatic story. Okay. Oh, I see. Happy, sad, and I don't know what this was gonna be. N story. So we're looping through story and we're getting scenes, I guess. Okay. This should fix it. Note that for loops also work on things called slices, which we'll see later. Yeah, they're just dropping in slices here without explaining anything about it. But slices are basically the thing you're actually gonna use, not arrays. Arrays are I basically never use arrays. I use slices. I mean, you have to use arrays sometimes if you want to have a buffer for something, but slices is the number one thing you're gonna use. Also note that for loops have recently become more flexible and powerful 2 years after this exercise was written. More about that in a moment. Okay. There we go. We got a dramatic story. Happy, happy, sad, and N. Happy. Okay, nice. 016 for 2. For loops also let you use the index of the iteration. Yeah. A number counts up with each iteration. To access the index of iteration, specify a second condition as well as a second capture value. So you can have a comma in here, which would basically create a range here. 0 ... means start at 0 and end whenever this ends. And I've never used more than 2 of these. I'm not sure if you can actually have more than 2 things in here at the same time. You probably can. And then you also, in the capture, the first one, you capture the first thing in the for expression there, comma, and then the second one. So you get the index. Well, I usually say I, but okay. You can name item and index anything you want. I is a popular shortening of index, and item name is often the singular form of the items you're looping through. Yes. Let's store the bits of binary number 1101 in little endian order, least significant byte or bit first. So it's kind of reversed. Yeah, value U30, so it's a 1011, but we actually want to say 1101. Now we'll convert the binary bits to a number value by adding the value of the place as a power of 2 for each bit. See if you can figure out the missing pieces. Okay, we're looping through bits, and I guess we want to have the index. Note that we convert a usize I to a u32 with int cast, a built-in function just like import. We'll learn about these properly in a later. Okay, what are they actually calling these? A built-in function. Is that the official name? Because I never know what these are called. We'll learn about these properly in a later exercise. So they are basically like very magical, these things here. They are not, you cannot define this, like you cannot have user defined as far as I know of these ones, but they're used to do certain things that will help you do things. In this example, we're using int cast, and casting, basically you change the type of the value. This is a specific to ints, so this is a usize which is casted to a u32. Now usize is always going to be u32 or u64, so it's either going to be the same type or it's going to have, you know, potentially more data. So this is potentially gonna lose data here if you do that int cast from a u64 to u32. Anything above, I think it's like 4.3 million, is gonna get truncated away. Okay, but I guess this shouldn't be an issue because I will never get over 4.3 million here. And so let's see, place value. Yes, so yeah, so this depends on, the place value depends on little or big endian. We're using little endian, so least first, which means we can just count from 0. Is it 0? The first one should be 1 or 0. Yeah, it should be 0. 2 to the power of 0 should be 1. 2 to the power of 1 should be 2, and so on. Okay. Value plus equals place value times bit. A bit is either 0 or 1. So if it's 0, this becomes 0. If it's 1, this becomes whatever, 2 times, or 2 to the power of n, where n is the place in the sequence. The value of bits, yeah. As mentioned in the previous exercise, for loops have gained additional flexibility since these early exercises were written. As we'll see in later exercises, the above syntax for capturing the index is part of a more general ability. Hang in there. This also, this reminds me of when I wrote a little bit of assembler code and had to make a, like, I had a problem where I wanted to print a number, you know, to the screen, to the terminal, and it was like, okay, this becomes a problem. There's no built-in function for this, so I have to, well, I didn't have, you know, the standard library or anything like that, or the C library or something, but so I had to like make my own algorithm for doing that. So this actually reminds me of that, because you had to sort of like loop through each value, like each number. I forgot how I did it, but actually I think I like divided by 10 or something each time. I don't know, I don't remember exactly how I did it, but let's see. 017. Okay, quiz time again. Let's see if you can solve the famous Fizzbuzz. Players take turn to count incrementally, replacing any number divisible by 3 with the word buzz or fizz, and any number divisible by 5 with the word buzz. So we kind of already did this, except in a different format before. Let's go from 1 to 16. This has been started for you, but there are some problems. Oh, well, this is one problem. So let's do that. Function. So main function should always be. It's kind of nice that they kind of remind you how it has to be. Like fn is function. You cannot type out function. Var I equals 1, stop at 16. What kind of loop is this? A for or a while? This is a while loop, I think, because we have this continue expression and a conditional expression there. And okay, so this should be fine. If it's, I mean, okay, so they could be both divisible by 3 and 5, 15 for example, so we cannot use else if here. My first idea was here to use else if, to not have to have these conditions here, but or you can maybe store them in variables. I don't know. I don't think that's like optimal anyway. Okay, if they are, okay, wait. If they are not, oh, we should print a number, I think it said. Wait, replacing number visible by word fizzbuzz. Okay, so we're basically saying, okay, we're counting, so this should be what we are saying. We're saying fizz, we're saying buzz, so here we should also say the number, I guess. If it's not divisible by 3 or 5. Okay, and the rest should be fine. Yeah. I wonder if they have a test. No, they don't have a test on this, right? Wait, do they remember which one we've done or not? Past? Okay, that's weird. Anyway, 018. I would like to look at the build zig file later. 018. Functions. We've already created lots of functions called main. Now let's do something different. Function foo. So you have the function, the identifier, parameters, return type, and a body. The foo function above takes a number n and returns a number that is larger by 1. Note that input parameter n and return types are both u8. Yes. The new function deep thought should return a number 42. Ah, I see. A reference. I think the supercomputer was actually called deep thought, if I'm not mistaken. Or was that like a real supercomputer? I don't remember. Okay, so we should make this function here. So function deep thought. We don't take any arguments. We return a U8 42 number curse of Douglas Adams, which is the author of Hitchhiker's Guide to the Galaxy. Please define the deep thought function below. We're just missing a couple of things. One thing that we're not missing is the keyword pub, which is not needed here. Can you guess why? Yes, well, I know why. It's because this is not. So public means you can access it from outside of this file. and we don't need that, so we don't need public. Main does need that because it's the main function. There we go. 19. Now let's create a function that takes parameter. Here's an example that takes 2 parameters. As you can see, parameters are declared just like any other types. Name type my function. Yes. Okay, the powers of 2. 2 to the 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Please give this function the correct input parameters. You'll need to figure out the parameter name and type that we're expecting. The number output has already been specified for you. Well, it's called my number because that's the only thing in there that's not defined. And I guess this is a U32 to not make things complicated. Standard math POW type AB takes a numeric type and 2 numbers of that type. And this is the first, I think this is the first time we're seeing in this little in this tutorial that you can actually pass types into functions, which is like mind blown thing. I mean, in other languages like C++, you would have something like this. You treat types very differently, or C# or Java or anything else. Yeah, or it could also be inferred by the type you put in, but that's kind of weird also. Like the standard library, sometimes they infer the type based on what you put in, or sometimes they say, hey, you have to say the type explicitly and then pass in a thing that's exactly that type. So that's kind of like a weird thing to me. It's like they kind of mix that convention a little bit, and I'm not sure if there's a purpose to that. Yeah, but that's interesting. So yeah, so this should run now. Oh yeah, I forgot to read this. Takes a numeric type and 2 numbers of that type, or that can correspond to that type, and returns a to the power b as the same numeric type is. So if you look at the signature here, we can see that we take a type as the first argument, and types always has to have the comp time keyword, and we're assigning it to the identifier t, and then we take 2 arguments that has type t. So that is the signature, and we return t as well, so that's the signature. So it's a generic function. Okay, now we're on to 20. Quiz 3. Let's see if we can make use of some of the things we've learned so far. We'll create 2 functions, one that contains a for loop and one that contains a while loop. Both of these are simply named labeled loop below. Okay, so we got a function main, my number 6, print the powers of 2. Okay, print powers of 2. You won't see this every day. A function that takes an array with exactly 4 U16 numbers. No, because this is a contrived learning example. This is not how you would normally pass. Okay, now they say this. This is, but yeah, this is true for all, like basically all of the examples in this here, in all tutorials basically. This is not how you would normally pass an array to a function. We'll learn about slices and pointers in a little while. For now, we're using what we know. This function prints, but does not return anything. Okay, it doesn't return anything, so this should be void, which is the keyword or the type that you would use in that case. And this one is a for loop because we're capturing something here from this array. Okay. Next one, this function bears a strong resemblance to 2 to the in the last exercise, but don't be fooled. This one does the math without the aid of the standard library. Wow. Yeah, so we'll just return, I guess we'll return a U16. Which may be dangerous depending on how large you want it to be. 8 to the power of, no, 2 to the 8. Well, that should be, U16 should cover that, yes. Okay, so that should be fine. Actually, yeah, I guess the result type doesn't matter because we're putting it in here, which can take any type. So we could put U32 here if you want. Here, U32, whatever. I'm gonna do it just to show that it should be possible. Except that we need to maybe cast. I don't know. I think sometimes Zig has implicit casts, but we'll see. If it's the conditions are perfect. We have this loop here. This should be a while loop because we have a continue expression here with a colon thing. So n equals number, or n is less than number n plus equals 1. Total is doubled. Yeah. And this is a very inefficient way, I think, to do this, because you can use the shift. I guess this might be like optimized into a shift. Actually, no. This is like, I think this, like this should be equal. We started 1. We shift every time we shift to the left. We should get times 2. Yeah. Or yes, and that's the same thing. Okay. Well, anyway. Return total. There we go. 32, 64, 128, 256. That looks correct. Okay, 1. I guess we should. No, I don't think the errors are helpful here to learn anything. Believe it or not, sometimes things go wrong in programs. But there is a very good thing to learn, like troubleshooting, because you're gonna run into problems. You're gonna have to read a lot of compiler errors, and you're gonna have to build some intuition around it to find what's the actual issue. I mean, usually it tells you exactly where to go. Sometimes you have to do a little bit of digging. So that is also a skill you need to learn as a programmer, like detective work on solving issues and compiler errors and stuff. Okay, believe it or not, sometimes things can go wrong in programs. No shit. In Zig, an error is a value. Errors are named so we can identify things that can go wrong. Yeah, okay. They're kind of introducing concepts here that you're kind of know what an error is. You know, if you have some background in programming languages, you would kind of know what they're talking about. But if you don't, this is gonna be, I think it's gonna, I mean, you can know what an error is, sort of, but it's not something tangible yet. You know that something is going wrong with a program, and you might get a prompt that says, or a message that says there has been an error, but you're not really aware of what they mean by error here. Errors are named so we can identify things that can go wrong. Errors are created in error sets, which are just a collection of named errors. We have the start of an error set, but we're missing condition too small. Please add it where it's needed. Here. Okay, so this is an error type, and you define it like this. You have error, curly brackets, and then a bunch of basically almost like an enum here. And these are now 3 distinct types of errors that you can have. I mean, this is kind of like a collection of errors, you could say. Yeah, error set, as they call it. And then these are the actual errors that you can get. So then we have, okay, we have an array of bytes. We loop through them, we print them. We say, is there a number error? Or we're getting some kind of number error. Okay, so this always returns an error. It looks like. So you're guaranteed to get an error. So either you're too big, too small, let's see. I guess we want to have too small here. Less than 4, more than 4, or we can be 2, 4. So we can't be right here. There's always some kind of error. Okay. And here we have the function here. Notice that the function can return any member of my number error set. Yeah, so you can define the return type as an error type or an error set, which means you have to return an error within that set. If you return an error outside of that set, that will be a compilation error. But yeah, so it's a good way of seeing that, okay, what kind of error can we get from calling this function here. And then another thing that I don't think, I'm not sure if they said it, but when you call a function that returns something, you have to use the return value. But if you don't want to, you can do this. And then if we comment this out, yeah. So if you don't do this, you will get an error or not. Yeah, but you do get an error here saying that you have to, error set is ignored. Yeah, so you have to do something here, but you can do this. Actually, no, since this is an error, it's a bit different. Okay. I guess they will probably go through this, so I will not do this right now. But anyway, yeah, there we go. All right. Yeah, it passed. Great. Now we're on to 22. A common case for errors is a situation where we're expecting to have a value or something that has gone wrong. Take this example. Text equals getText full.txt. What happens if getText can't find full.txt? How do we express this in Zig? Zig lets us make what's called an error union, which is a value which could either be a regular value or an error from a set. Vartext equals, or vartext my error set exclamation or bang text equals getText full.txt. For now, let's just see if we can try making an error union. So we have a error set called my number error. We have an error called too small, and this guy is assigned to an error down here, so we presumably want this error type, but it's also assigned to a 5, so let's just make it into a byte. So this variable can be either an error or this byte here, and here we are setting this to an error, so it's always gonna be an error. Looks like my number will either will need to either store a number or an error. Can you set the type correctly above? I think so, yes. Alright, error 3. One way to deal with error units is catch any error and replace it with a default value. Foo equals can fail, catch 6. If can fail fails, foo will equal to 6. if can fail fails full will equal 6. Yes. So here's the introduction to the catch keyword, which is used if you have an expression here that's an error union. You can use catch to say basically this is the same as saying const a equals if this is equal to basically this. It's almost the same as saying this. It's catching all the types of errors, but if it's this error, if it's an error, is there like an is error or something? No. Then where the result is 22, otherwise I mean, we're kind of capturing this value, the return value, so let's just, it's kind of the same thing as this, right? So we're either, if it's an error, we're using 22, this here, or we're using the actual value that it was. And here we just say catch to make this work here. Please provide a return type from this function. Hint, it'll be an error union. Okay, well this will be a my number errors thingamajig, and an or u32. Yes, so now we're on to 24. How many are there actually? 100. Okay, 100. Is there 200? No. 110. Okay, so 110. Wow. Guess I have to pick up the pace a little bit. Using catch, because I would like to complete this to get basically all the bases covered with Zig. And the one thing that I've learned so far is the while continue expression. I had no idea about that. Maybe I should go through sometime the Zig docs and just read everything. Using catch to replace an error with the default value is a bit of a blunt instrument since it doesn't matter what the error is. Oh, okay. Yeah. So this goes into different types of errors and having like handlers for different types of errors. And here we're using an if to check if error is equal to some kind of error here. So you can check if error is equal to something else. And my number error, too small, too big. The catch 0 below is a temporary hack to deal with make just right returned error union for now. Okay. In this silly example, we've split the responsibility of making a number just right into 4 functions. Make just right, calls fix too big, cannot fix errors. Okay, fix too big calls fix too small, fixes too big errors. Fix too small calls detect problems, fixes too small errors. Detect problems returns the number or an error. Okay, make just right calls fix too big and cannot fix errors. Okay, well that seems to be what it's doing. Fix too big, fix too small, calls fix too small, fixes errors. So if it's too big, we return 20. Okay. Fix too small. Okay, here we go. This is missing a lot. So it's near identical fix too big above. If we get too small error, we should return 10. If we get error, we should return error. Oh yeah, so we detect problems. We're catching an error, so we can capture the error, and we can make a code block here, and we can say if error is equal to too small, we will return 10. Otherwise, we return the error because we couldn't fix it. and otherwise we return the U32 module. Well, we're doing that because we're returning this if it's not an error. All right, that worked great. 25. Zig has a handy try shortcut for this common error handling pattern. Can fail, catch error, return error, which can be more compactly written as try can fail. Now you might wonder why you want to do this, and that's because you're basically bubbling the error up to the next caller, and it's kind of a way of explicitly saying that we need to bubble this error up. I'm not going to handle this error. Whatever caller is calling this function should handle this error, which is something that happens implicitly in a lot of other programming languages like C#, C++, I'm pretty sure, and yeah, basically almost all other that has like exceptions. You have to wrap something in a try catch to actually catch the error. Otherwise it's implicitly bubbling up to basically the main function, and then it just crashes. But here in Zig, you have to explicitly handle all errors, which is great because it's easily handled, and it kind of forces you to actually handle stuff, which is good because yeah, you want to handle things, which can be more compactly written that try can fail. Yes, so this catch error, return error is just try can fail. So if it fails, it bubbles up to the caller, and the caller has to deal with the error. And here we're calling add 5 catch 0. Okay, add 5. This function needs to return any error which might come back from detect. Please use a try statement rather than a catch. So try in this case needs to be here, since that call to detect is the thing that can return an error. So you put try before that, and now this becomes the catch error, return error. Let's do that. I wonder if they have an actual, like if you would say this catch error, return error, if they would like fail this test or here, or because there's basically no difference. You would have to sort of inspect the code to see if we used the correct thing or not. Okay, let's move on. Great news! Now we know enough to understand a real Hello World program in Zig. Oh, I see. So they were building up to this to print in a real quote-unquote way. One that uses the system standard out resource, which can fail. Yes. Excuse me. Take note that this main definition now returns bang void or exclamation mark void rather than just void. Since there's no specific error type, this means that Zig will infer the error type. So it basically can be any type of error except, yeah, it's inferred by whatever errors is can be thrown in or returned in the function. This is appropriate in the case of main, but can make a function harder, function pointers, or even impossible to work with recursion in some situations. Yeah, but it's very convenient if you don't want to type the error out as well. You can find more information at blah blah blah. So it does make it a little bit less readable, I guess, but because to find out what the error can be, you have to go and look at all the calls inside, and then to make an error set of all those. But anyway, some standard library functions do that actually. We get a writer for standard out, so we can print to it. So this is the thing here, like to be able to write to stand it out, you create this writer. Actually, is this still working like this? File writer. This is a file writer, right? Oh, I see. Yeah, so this is updated for 0.15, I think it was. Before, you didn't put interface here, you just had like standard out print. It's a bit different now, you can just say print hello world. Although, I'm pretty sure you had to have a buffer here. But they just put an empty slice there. Or, yeah. How does that work? I thought you had to have a buffer. Defaults to positional read. Okay, this I didn't know about this. I did not know that you could put an empty slice here. That's okay. Interface. Okay, send file. Okay, yeah, because this is file. Drain. It's just incredible to me. I didn't know that this was the case. Where, so... Wait, the buffer is stored. Hang on, where was the buffer stored? In the IO writer, okay. And so this one. Oh, that's a reader. Oh yeah, so you okay. You have to have a reader. Oh, okay. Print, blah blah blah. I just want to check this because it's pretty interesting. Writer to a file. I guess maybe because it's a writer might not need a buffer. I don't know. Okay, whatever. This is too complicated to look at right now. Yeah. I didn't know that you could put an empty slice. I thought that you had to have some sort of buffer that it would use in memory to do stuff. But okay, that's a new one as well. Maybe I should write down new things that I've learned from this. New things learned. Okay, so this would be first off is while continue expressions, which is while and then like n is less than 6, n plus equals 2. And then what is, yeah, writer, file writer does not need, well, file writer can be called with an empty slice. Okay. Did I fix it? No. We get a writer. Unlike standard debug print, the standard out writer can fail with an error. We don't care what the error is, we just want to be able to pass it up as a return value of main. We just learned a single statement which can accomplish this, which is try. There we go. Hello world. Oh, it does have tests here, so it's testing the output. Okay, so now we're at 27. Why did this get scrunched up here? Okay, let's do... oops. This. Okay. You can assign some code to run after, I should say, like ziglings tutorial. You can assign some code to run after a block of code exits by deferring it with a defer statement. Oh yeah, defers, okay, yeah. So this is a code block, the curly brackets here, or braces, I don't know which is the correct term. Defer, run later. So this will run at the end of this scope, or this block here. So it will run after run now. In this example one, run later will run when the block is finished. So a code above would run in the following order, run now, run later, yes. This feature seems strange at first, but we'll see how it could be useful in the next exercise. Without changing anything else, please add the first step into this code so that our program prints 1, 2. Alright, defer that. I was just checking the new line was correct. Yes. Okay, 28. Now that you know how defer works, let's do something more interesting with it. Okay, so we got some animal shortcuts here. G, C, D. I'm guessing goat, cat, dog, zebra. Like this function is supposed to print an animal name in parentheses like goat, but we somehow need to print the end parentheses. Even though this function can return in 4 different places. How? I'm guessing we can put defer here. So we first print this, we defer that. Yeah, so this is a good example of defer, the power of defer, because it's gonna happen when we return. So we can return from, so we don't have to put this in every place we return, which is a very nice feature. We can just put it at once up here, and it will happen every time we return, or any time we return, no matter where we return. So we have goat, cat, dog, unknown. Okay. Yay. 29. Another common problem is a block of code that could exit in multiple places due to an error, but that needs to do something before it exits, typically to clean up after itself. An error defer is a defer that only runs if the block exits with an error. So we have a block of code, error defer, clean up, try, can fail. So if can fail fails, error defer will call cleanup to clean up any things that needs to be cleaned up. The cleanup function is called only if the try statement returns an error produced by can fail. Yes, okay, we have a counter, error, get fail, inc fail. We simply quit the entire program if we fail to get a number. Okay. Make number, getting number. Please make the failed message print only if make number exits with an error. defer. Fail. Yeah. So this doesn't seem that impressive right now, but it's gonna be a very good tool to use if you need some cleanup to happen, like freeing up some allocation made that was going to be used throughout the function, but now doesn't need to be there, so we can clean it up only if there's an error. Like, let's say we're creating a new resource and we're allocating a bunch of different things to create it, but then somewhere along the way we fail, so then we need to clean up after ourselves, which defer is a nice way of doing that. Okay, yes, this can fail, great. Alright, I could fail, but I don't. I fail, okay. Okay, that seems to work. Now we're on 30. The switch statements let you match the possible values of an expression and perform different actions for each. The switch... Yeah, so if you're familiar with programming, you probably know what switch is. It's another way of writing if. A bunch of else cases, else if. But actually, yeah, switch in Zig has a bit more use as well, especially in 0.15. They added you can have labeled switch, and you can sort of make it like a loop in the switch, like a state, almost like a state machine, which is interesting. I haven't really used it that much, but yeah, it's a very interesting thing. Okay, but that's more advanced. Here's just a basic thing. So we have switch players. If players is 1, then we start a 1-player game. If players is 2, we start a 2-player game. Otherwise, we call alert and return an error. Yeah, and here's the if-else equivalent. This is basically the same thing. Logically. Okay, so wow, here's a bunch of switches or cases here. Okay, so we have like characters, A, B, C, D, blah, 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 blah. We don't need everything here in between. Okay, fine. Switch statements must be exhaustive. There must be a match for every possible value. Yeah, which is very, very good thing, because it's also a thing. It forces you to complete the code basically, and also if you add more possible cases, you then get compiler errors, which tells you, hey, you have to implement these cases, and it points you exactly where you need to go in order to fix the problem. So I think that's a very, very good feature for safety in the code. Yeah, there must be a match for every possible value. Please add an else to the switch to print the question. Yeah, okay. So, you know, kind of like an anti-pattern to that is to have an else which catches everything, and now you don't need to implement more cases. So you have an else to this switch to print a question mark. Okay. So we'll print a question mark there. All right. And sig question mark. Great. 31. What's really nice is that you can use the switch statement as an expression to return a value. Yeah, so really, I really love this about Sig, that they take almost, I think, all of these classical statements like if statements, for statements, switches, while loops, everything can be an expression as well. So you can use this as an expression, and whatever result it will be can be put into A, which is really nice. I mean, it's just a more convenient way sometimes to get a value out.
I would rather have this than not have it. It's just a nice feature to have. I mean, otherwise you can just, you know, you have to say like var a and then the type. For one, it's now you have to say that it's a mutable, and I don't know, it equals undefined. Whoops. And then here you would have to say switch, and then a equals. So it's just, you know, this is so much better. Sometimes I wouldn't use it all the time, but you know, it depends. It always depends. Okay, so we have the same basic thing here as in the last. Please set an exercise. This time turn a exclamation mark. There we go. Also, see how we don't have to call the thing every branch. We can return this value instead and then call one time here. So it becomes a lot clearer as well what's happening. Note C forces print to display the value as a character. Can you guess what happens if you remove the C? It will print it as a number. I'm pretty sure. Yes. That is a huge number. I guess it's like UTF-8 maybe. What? Zig. Okay. Okay. Whatever. 32. Unreachable. Zig has an unreachable statement. Use it when you want to tell the compiler that a branch of code should never be executed and that the mere act of reaching it is an error. Yeah. I mean, in this case, it's kind of implicit here because you have like if true, you don't have to have an else unreachable. But yeah. So basically, if you, as a programmer, you can see that okay, there's no way of reaching this point. You can add unreachable to tell sort of the program or the compiler that, for example, if you're in a function that returns a value, well, here you don't have to return a value because this is unreachable. So, for example, here we made a little virtual machine that performs mathematical operations on a single numerical value. It looks great, but there's one little problem. The switch statement doesn't cover every possible value of a U8 number. We know that there are only 3 operations, but Sig doesn't. Use the unreachable statement to make the switch complete, or else. Or else what? Operations 111322. Yeah, so here we see this. Current value is 0 operations. Okay, so we're looping through the operations, which is comp time known. I'm not sure if they think about you have to think about that now, but operations, operation, switch on operation. If it's 1, we add 1. If it's 2, we subtract 1. If it's 3, we multiply, or we square. Yes. Okay. What's the issue? Oh yeah, we need to add some kind of unreachable. Okay, so okay, I see. So basically it's saying that this switch is switching on a U8, so it's saying that okay, well you have 1, 2, and 3, but this input can be up to 255 or 0. So where's those cases? So we can say else unreachable because we know that that's gonna be the case. Now interestingly, this could be a thing that the compiler could figure out, because this is compile time known. Yeah, but anyway, There we go. Passed. Okay. 33. If error. Oh yeah, this is a feature that I never use basically, but it's interesting. Let's revisit the very first error exercise. This time we're going to look at an error handling variation of the if statement. If foo value. So when you use a capture like this, like you can have if value and a capture, this value has to be either an error union, in which case you would capture if it's not an error, and then you capture the value, or it can be, which you haven't gone through here yet, but it can be an optional as well. So it can be null or a value, and here is like it's not null, so you get a value out. But here you can have else. If it's an error, then you can capture the error here and do something with that. Okay, we'll take it even further and use a switch statement to handle the error types. Yes, you can switch on an error to switch on the different types of errors instead of using an if, which they did before. But switch is usually much easier to use. My number can fail. So this could be an error. So n can be an error here. Too big or too small, or a U8. If it's not an error, we are in here and we're printing it out. If it is an error and we're switching and looking if it's too big, then we print this. Right, so they want to have a case for too small. And since that is all the cases of this switch, this is, okay, this is also a nice thing. So I'm going to show, so this error can be either too big or too small. So we're covering all of the cases here, so there's no issues. But if we would implement more things now, and now we suddenly have another error called 2, 0 or something. Now we get an error at this switch statement here that says that we're not handling the error value to 0. So you kind of get this compiler help from the compiler to actually tell you, hey, you need to implement this here. You need to, like, you added a new thing here, so now you need to implement it, which is really nice. I really like that. That is an incredible feature. Okay, yes, so this one should now be, this time we'll have number maybe fail, return an error union rather than a straight error. Okay, right. So now that should be fine. Okay, now we're on to 34. Quiz time. See if you can make this program work. Solve this any way you like. Just be sure the output is my num equals 42. My underscore num equals 42. Okay. I can solve it any way I like. Okay. Cool. They just don't they don't tell you straight up how to do it anymore. Great. This function is obviously weird and non-functional, but you will not be changing it for this quiz. Oh, really? Okay, so get number is if false, return num error illegal number. So it's just to, you know, potentially return an error, except it doesn't return an error because it always returns 42. So this one, so since we're so we can solve this in a number of different ways. What you could do is you can say this is num error that. You can also not leave that out if you want, and then later here you can say well, you can do this. You can say x equals if my num value, so value, else 42, but that's very convoluted, and then you can replace this by x. So now we make sure that x is always 42, but that's very convoluted, so I think a very more nice way to do it is just catch 42 here, which will do basically the same thing here. So if this is an error, the result will be 42. Otherwise, this is gonna be 42 here. I mean, it's kind of weird because they're saying make sure the output is 42. I mean, we could just put 42 here. I guess. 34. Wait. Oh, okay. So we're trying. We have to add an error union here because we're trying to print, which will be an error. All right. There we go. My num equals 42. So 35. Remember that little mathematical virtual machine we made using the unreachable statement? Well, there are two problems with the way we were using opcodes. One, having to remember opcodes by number is no good. I agree. Two, we had to use unreachable because Zig has no way of knowing how many valid opcodes there were. And enum is a Zig construct that lets you give names to numeric values and store them in a set. They look like error sets, and it's also your best friend. We have an enum with apple, pear, and orange. Also to note about enums is that each value in here also has a numeric value. It's usually, I think, like a U64 maybe? On 64-bit systems. I think it depends maybe. But it's like the first is 0, then there's 1, and then it's 2. And you can also assign them values if you want. But it's also good to know. And you can convert ints to enums and enums to ints. Or strings to enums also. Okay, so my fruit equals fruit.apple. Let's use an enum in place of numbers we were using in the previous version. Complete the enum. Okay, so we can see here what they should be. Ink, power, deck. I think maybe I can actually use... Whoops. Wait, why is it... Why is it doing that? Or is it doing that because of the way I'm pasting it? Okay, well. And then we can do this, and we can say, actually, is there like a unique, distinct? No, maybe there wasn't. Okay, whatever. Let's just do this manually. And then we have to add that. Okay. And you can also, that's interesting about the formatting. If you remove the comma and save format, it formats it like this. If you add a comma at the end, it will format it like this. So depending on how many, you know, how long the line is, you might want to do one or the other, but it's always gonna follow that rule, and that's really nice. Okay, so we have that, and otherwise it's like doing the same thing. No else is needed. Why is that? Because there's only 3 options now, which is really nice. So we have ink, deck, and power. I would call that squaring. No else is needed, yes. Great. Passed. 36. Enums are really just a set of numbers. You can leave the numbering up to the compiler, or you can assign them explicitly. You can even specify the numeric type used. Yeah. Yeah, so you're just like I said here, and yeah, also, okay, I kind of missed this. So you can also specify the type that they call the backing integer type of the enum. So yeah, so now this is a U8, and I'm not sure which it will be by default, but I think it depends on if you're 64-bit or 32-bit operating system. Anyway, and here you can also assign the value as well. You can, which is probably not that usual to use, because there is a point in having, 0, 1, 2, 3 representation of the fields, because then you can kind of loop through them. However, you can use comp time magic to loop through enums as well, so you don't need to do that. But anyway, you can get the integer out with a built-in function, int from enum. We'll learn how about built-ins properly in a later exercise. Oh, yeah. So here's int from enum. Yeah, as I said, you can turn int to enums, or vice versa. So this one turns this into an int, which will result in 16 here, because foo is assigned to 16. Note how that built-in function starts with @ just like the @import function we've been using. Yes, it's basically magic functions that only the compiler knows about, or you can't define those functions yourself. And yeah, they're kind of weird, but it's like a way to not have a bunch of weird keywords, but instead have a way to sort of have special functions that can do almost anything. I mean, there's no like real, I guess, how you would say, there's no theme to what they do. They just do a bunch of random stuff, like casting. There's even math functions like cosine and sine. There's like type coercion stuff, and math functions. What else is there actually? Yeah, and then there's like you can do some set compiler flags and stuff with those, and change some weird stuff with it. But anyway, excuse me. Zig lets us write integers in hexadecimal format. 0xf. This is the value 15 in hex. Web browsers let us specify colors using hexadecimal number, where each byte represents the brightness of the red, green, or blue component, where 2 hex digits are 1 byte with a value range of 0 to 255. Well, this is not a valid hex, but I guess it shows which color is which. Please define and use a pure blue value color. Pure blue. Oh, I see. These are different colors here. Okay. So 0000FF is blue. You usually also have a alpha component, but yeah, this is actually not a 32-bit. This isn't it? Wait. I mean, okay, usually you have like the last two being the alpha, but I guess in this example we don't have that. Main, remember Zig's multi-line strings. Here they are again. Also check out this cool format string. Yeah, you can have weird format specifiers like this. X means hexadecimal, even lowercase. I think capital X means uppercase, hexadecimal. I don't know what this is. This is a new thing. New thing alert that I learned from this tutorial. Needed for format syntax. Oh yeah, this separator here. Padding characters. Default is 0. Okay, I knew about padding. So basically, like if you want to print out minutes and hours, you can use padding to easily add a 0 if it's like a 1 digit. If you want to print like 0, 1, 0, 2, 0, 3, 0, up to 0, 9, and then 10 will become 1, 0, 1, 11. So it's a nice way of doing that. But this one, aligns right. And then width. Oh. Use padding to force width. Okay, I don't understand the last part. Use padding to force width. Okay, I didn't know about this. This is really cool, actually. Aligns right, so, and the width is 6. Use padding to force width. I guess what they're saying is if you have padding, that will count to the width of the thing. I don't know. Please add this formatting to the blue value. Even better, experiment without it or try parts of it to see what prints. Experiment without it, try with see what parts, try parts of it. Parts of it. Oh, I see. They're speaking about down here. So the width is 6. Oh, I see. Okay. So basically, since we're not specifying the whole number here, I mean it's implicitly 2 zeros at the start here. So it's FF0000, but the real, like the full value here is 00FF0000. So we're actually, because it's a 32-bit number, we're then using four sets of 2 hexadecimal numbers. Each 2 is 1 byte. So this is 3 bytes only, but 32 bits is 4 bytes. 4 times 8 is 32 bits. And here we're saying insert the 2. So this is inserts the first 2 zeros. So if we say the width is 4, we should see the blue. No, wait, 4. Hang on, this should be 8, right? But they're not. They're okay. No, okay. I'm stupid. They were talking about the CSS value here, which yeah. Okay. I mean, you can put alpha in here if you use RGBA, but yeah, this doesn't exist. I don't think in CSS. But okay, so this is like 6. This will print the correct hexadecimal. So all the things I'm talking about, the alpha, that was more like if you're working with graphics programming in C++ or something like usually like game programming. Yeah, we passed. Okay, let's just continue. So actually, yeah, I'll put this as a new thing that I learned. Number formatting with like align right and width. I mean, I guess you can use D as well, and then well, let's use X. I'll just do this. Align, so this is align right and 6 is width. Okay, I'm just putting down notes so I will kind of remember this later. Okay, on to the next one. 37. I think this one 37, yes. Being able to group values together lets us turn. So now we're on tuples. No, structs, I mean. 0.1_x. Yeah. Yeah, so you would group this in a struct that has x, y, and z as fields. And then you can define them like so. If you have this point struct, which we don't, it's not defined here yet. I wish they, I mean, okay, they're defining it down here. Point above is an example of a struct, shorthand for structure. Here's how the struct type could have been defined. Yeah. Let's store something with a struct, a role-playing character. Now you're speaking my language. We'll use an enum to specify the character role, wizard, thief, bard, warrior. So here's an enum role. Please add a new property to this struct called health and make it a U8 integer type. Health U8. Oops. I mean U87 also works, but U8 is probably enough there. So we have role, gold. That's a lot of gold you can have. Experience and health. Okay. Initialize Glorp with 100 health. Glorp is a wizard with 20 gold, 10 experience, and 100 health. Glorp gains some gold. Yes, and Glorp is crucially a mutable character, which means you can change the values. And then takes a punch. Health minus 10. The wizard has health and gold. Great. Nice. Alright. 38. Grouping values in structs is not merely convenient. It also allows us... I should say that like that whole exercise, like these exercises with the, you know, characters and, you know, printing things to the terminal. This was like the first thing that I learned. Like, I mean, yeah, it was almost like 30 years ago when I started learning. Like, first you had to learn just to make a program, but then you started with like printing things to the console or terminal. And the first like project was like making a text adventure game. So that is very yeah, nostalgic for me. And also I mean, I think it's fun to do as an exercise sometimes. Grouping, like doing it every now and then to kind of see like how would you structure the program now with your current like experience and knowledge. Grouping values in structs is not merely convenient. It also allows us to treat the values as a single item when storing them, passing them to functions, etc. Yes, this exercise demonstrates how we can store structs in an array, and how doing so lets us print them using a loop. So I have the same stuff here as before. Two characters now. So we have an array of characters that is not set at the start, and now we set first one here. That's the same guy, and then we have Zump the Loud with these stats. Feel free to run this program without adding Zump. What does it do and why? Okay, well, we're looping through all the characters. Now keep in mind we set them to be undefined, and then we only set the first one. So the first one has proper values put in here. The second one is gonna be whatever garbage is in that place when we run the program. So it should like, yeah, it says, even says here garbage values. In debug mode, which is default, sig writes the repeating pattern in binary to all undefined locations and make them easier to... Oh, wow. Okay, I didn't know this. What the hell? This is really good information, actually. This is incredible information. I'm gonna add this here. Undefined values. I guess comp time known undefined values will print to 10101010 or in hex. Because I've seen that a lot and I was like, what the hell is this? Okay, this is AA. I think if you have a pointer that's undefined, it might fill it up with A's. I'm gonna do this. Wow, that is very good information, because if I see this next time I see this, I will know that it's actually a pointer or something that is undefined. Or a value. I usually never have this with values. I usually only have this issue with pointers, which is also interesting. But yeah. So if we print this now, we will get some garbage values. I guess this would be like the equivalent of. Yeah, you can see it's like the same value. This is probably the like the decimal representative of this value here. And this is also one, but with a lower amount of space. Actually, no, but let's do that, and we will do this. Whoops. Okay. Actually, I will do this. Okay. So there we go. Yeah. So okay. So let's fix this. Then we can simply do this. Say chars 1 equals. Print this here, and you always need a dot at the start. Actually, let's do a macro and that. All right, save. We don't have a okay, we need row of bars. There we go. Alright. That should be fine. Yeah. Now we're on to pointers. Ooh. Now we're going into the dangerous territory. The territory that probably makes you spend the most amount of time debugging and thinking about what the hell you're doing. Check this out. Var foo u8 equals 5. 5 is a value. Foo is just a u8. Bar is a magic star u8, and we set it to this weird symbol here, foo. This means the address of foo, or a reference to foo, depending on what you call it. Bar is a pointer. Yes. What is a pointer? It's a reference to a value. In this example, bar is a reference to the memory space that currently contains value 5. I mean, yeah. Yeah. A cheat sheet given the above declaration. U8, the type of a U8 value. Foo has the value 5. Foo is an identifier, I would say, but okay. And then star U8 or asterisk U8, the type of a pointer to a U8 value. Ampersand foo is a reference to foo. Yes. Bar, a pointer to the value at foo. You can also say ampersand foo. It means the address of foo, the memory address of foo. A pointer to the value at foo. Bar dot star means you dereference the pointer which grabs the value at the location where bar points to. So it points to foo, so it will grab the value that foo has. And now, why do we even need this? We'll see why punctures are useful in a moment. For now, let's see if you can make this example work. We have a num1 u8 equals 5, num1 pointer, yes. Num2 is undefined. Please make num2 equal to 5 using num1 pointer. Yes, so you would, since num1 is 5, you could dereference this to make it 5. Yep. Great. But we still don't know why we want to use it in this tutorial here. It's important to note that variable pointers and constant pointers are different types. Okay. Oh yeah, variable pointers and constant pointers are different types. So the address of foo or reference to foo is of type pointer to u8. Reference of bar is of type ref or pointer to a constant u8. Since bar is constant, yeah, it doesn't lose its constantness, so you can't use a pointer to, for example, modify bar like this. You can always make a const pointer to a mutable value, but you cannot make a so that would be a constant pointer to a mutable value. That means you can't change the pointer, where the pointer points at, but you can change the underlying value that it points to. But you cannot make a var pointer to a immutable value. Oh, they were talking. Okay. So okay, no, scratch that. I was saying, like, you can do that as well, but this means what they mean here is you make a pointer that you're saying like, hey, you can't change the contents of this pointer, even though the contents is mutable. But you cannot make a mutable pointer to an immutable value, a const. It's interesting they mix the mutable and immutable terms in here. I guess it's good to know that it's called immutable and mutable. Make var pointer to a mutable value. Yeah, so you can't make a constant, like you can't remove the constantness of a constant by using a pointer. This sounds like a logic puzzle, but it just means that once data is declared immutable, you can't coerce it into a mutable type. Actually, you kinda can, but it's yeah, it's not a good idea. Think of mutable data as being volatile, or I think you can actually, but because you can basically cast. I think you can basically cast anything to anything, but yeah, it's not a really good idea. Think of mutable data as being volatile or even dangerous. Like the normal constructs that you would use in everyday programming doesn't allow you to do it. Zig always lets you be more safe and never less safe. I mean, not entirely true, but okay. Yeah. A equals 12, B equals this. Pointer, okay. Yeah, so you have to, so now the type is wrong. You have to say that this is a const there. Yeah. And then use the reference. Okay, 41. Trick about the pointer's mutability or as const refers to the ability to change what the pointer points to, not the ability to change the value at that location. Yeah, pointers kind of have a duality of them like that. And in C, it has even more nuance to it, and C++, yeah. Anyway, const locked equal u8 equals 5, or unlocked u8 equals 10. Pointer 1 points to locked, pointer 2 points to locked as well. So this is a constant pointer pointing to a constant u8. So you can't change the location where P1 points to. You can't make it equal something else. Pointer 2, you can make it equal something else, but the contents to where it points to can't be changed because it's constant. Both P1 and P2 point to a constant values which cannot change. However, P2 can be changed to point to something else and P1 cannot. Yes. And here we have a constant P3 to a mutable U8 which points to unlocked, so there's no problem there. Pointer mutable P4 points to mutable unlocked. Constant P5. Yeah, so here you can specify that this should be you can't edit the contents of this pointer to where it points, like yeah, and but you can still reference mutable values. Oops. Which is good because then you can have a function that takes a pointer to a constant, so it's kind of saying that, hey, I want a pointer, but I'm not gonna change the contents of whatever's in there, and then you can put a mutable value in that argument, and you can be sure that this function won't change the contents of that pointer, but you can pass it as a pointer for if you want to make sure that it works. P3 and P4 can be used to change the value they point to, but P3 cannot point to anything else. What's interesting that P5 and P6 can act like P1 and P2, but point to the value at unlocked. This is what we mean when we say we can make a constant reference to any value. Yes. Foo equals 5, bar equals 10, both are mutable. U8, please define a pointer P so that it can point to either foo or bar and change the value it points to. Okay, so it can be mutable. It should be able to point to any of those. I mean, they have the same types, so there's really no difference. And since we're adding it here, we should make it mutable. Alright, so first we're setting it to address of foo. We are dereferencing, we're changing foo at this point. Here we're setting it to bar, and we're saying changing bar. Great. Now we're up to 42. Now let's use pointers to something we haven't been able to do before. Pass a value by reference to a function. Why would we wish to pass a pointer to an integer variable rather than the integer value itself? Because then we are allowed to change the value of the variable. Yeah. Pass by reference when you want to change the pointed to value, otherwise pass the value. Yeah. So basically here, this function's purpose is to change the original here, which is this one, and then you pass address to make sure that this function can change this here. And if you would pass it as this, it would be just a copy, which wouldn't change the original. And this function should take a reference. Yes. So we have to dereference, set it to 5. That will make it to 5. Now something interesting. Let's pass a reference to a specific array value. Yeah, so an array is kind of like in C, arrays are basically pointers. Here they are kind of, I mean, different, maybe. Yeah, I haven't used arrays, that, to be honest. I'm using slices most of the time, so I'm you know, there's very few use cases where I actually use arrays, but I don't think you can do like pointer arithmetic the same way as you can with But you can always turn a pointer into an integer and then do arithmetic if you want. Anyway, like in C, you could say more nums plus 2, and it would sort of mean the same thing as this here. I think, I'm pretty sure. Okay, well anyway, so this accesses the second element. So normally if you didn't have this, this would produce the value where this address points to, or the second element in the list or in the array. This will return the address of the second element in the array. And then we print all the numbers in the array. Okay. That worked. Okay, now we're on to 43. As with integers, you can pass a pointer to a struct when you will wish to modify that struct. Pointers are also useful when you need to store a reference to a struct, a link to it. Yes. I mean, basically everything has an address except for constants. Well, I guess constants can still have a reference. I mean, they do have an address. It depends it depends, I guess, a little bit on, you know, you can have a compile time constant. There's also the concept of read-only memory in the program. But yeah, basically everything has an address, so except for the types, I guess. Wait, can you have pointers to types? No, that would be weird. I'm gonna set you to character. Oh, let's fix the thing first here. Please pass glorp to print character. You need a... Okay, you need a reference, so let's do that. Wait, it worked? Wait, so you can have a pointer to a type? It has to be comp time, and then value is td referenced. No, this doesn't. This shouldn't work. Yeah, it loses the thing there. Okay, let's go to the next one and I'll try that again. 44. Wait. Let's do elephant. Okay. Let's fix this first. Elephant B doesn't exist. Okay. There you go. Except I'm gonna say this so we don't succeed. What the hell? Okay, so let's do hello value, and we'll call this function with hello and hello. Oh, except this doesn't work because it needs to be an elephant. Let's do this. Let's do like we set any here, and then hello is an elephant, so we have to put an elephant here. And well, let's just put elephant A. Okay, there we go. Oh, I see. It needs to be. So you can have pointers to types. I didn't know that. Would that be something useful? Maybe. This needs to be. So this is a mutable pointer. Expected type. Oh, so this is like a constant type because you can't have a variable type. I'm pretty sure. Variable of type const of no, variable of type must be const or comp type. Can it be comp time var? Wait, is the var comp time var? Hang on. You can make a comp time block. Things happening here happens in comp time. Let's have a var s equals struct a u8 s. Let's do okay. Yeah, it's never mutated. How do you mutate it? Like you could set it, I guess, to B? No. This is weird. Wow, okay, it works. But it's only like in a comp time context. So it has to be in a comp time. But I think you can have like comp time vars. Yeah. Or did they remove that, actually? Maybe they removed it. I think maybe they removed this feature. Okay. Alright, so you can do some weird things, like you can have a mutable type like this. But it's like, and in this scope, S means something, and here it means something else. So it's very confusing, because usually types are, you know, constant. Okay, well, yeah, okay. So basically here, having like a, whoops, this needs to be a const type. Or you could say comp time, maybe comp time. No. So this is a const type. So this, I mean, basically this is no different from just passing the type like straight up. Actually, if we put the, if we make this into a var, and we'll take a function, a thing here, a value should be the point that the type is dereferenced hello. And then let's remove this. We call this. So now, since this is a mutable pointer, I'm gonna guess you can't have this. But since this is a mutable pointer, you can change what type this points to, which means this function will change its type. Well, I'm guessing this doesn't work, but yeah, okay. Variable that points to constant type must be constant comp time. Okay. I see. But can you have it in a comp time scope? I can't define functions in here. Yeah. All right. But actually, you can have a struct. And that you can have hello test2 equals this. Let's remove this. And then type of hello test, which is a function, return type, type name. So we'll print the return type, and then if we change this to something else, B, this is so stupid, but and then we print the same function again, what happens? Hang on. Okay, let's remove this. No member. Oh, this needs. Oh wait, this needs to be 2. I'll make this public just in case. Here we go. No, it points to the same type. The return type. Okay, so it didn't change. So it's kind of like this, kind of like the code is executed in sequence here, like this. The value of this, whatever this is. Okay, so then if you make a new function using the same pointer after this has changed, you make a new one called hello test 3, and then this would be hello test 3. Now it should be okay. Now it's different. Okay. Okay, I didn't know this, but I don't think I'm gonna use it anytime soon. Okay. All right. Okay. Anyway, let's continue here. Link the okay, so what is happening here? Elephants are walking along the trails, holding hands by holding tails. From holding hands by Lenore and Link. Okay, we got an elephant with a leather tail and elephant. Oh, I see. It's like pointing to another elephant, maybe. Hello, Vicent. Seems cursed. Yeah. Yeah. And I would say it wouldn't be good if you could change, like have a type that sort of changed over time. Visited bool equals false. Yes, so we've got link alphas and point to next alpha. They make a circle. A, B, C, A. Okay, A points to C. Or B, I mean. Elephant. B points to C. C points to A. And A points to B. Okay, now it's all set up. And now, what is this? This visit elephants. This function visits all elements one, starting with the first element, following the tails to the next. So it's like a linked list. A singly linked list, I think, is what it's called. If we did not mark the elephants as visited by setting visited equals true, then this would loop infinitely. Except in a real, I guess, linked list, you would have the tail be optional. But yeah. Okay, so we need to mark them as visited. Okay. Alright. There we go. It's done. Great. 45. How's it going, Vincent? Sometimes you know that a variable might hold a value, it might not. Sig is a neat way of expressing this they called optionals. Yes, an optional type decision. Alright, I'm gonna try and complete this as fast as possible now. I want to like explain a whole bunch, so I'm just gonna try and finish this to see if I can learn more stuff. Okay, now Foo can store a. So I'm gonna read through everything because I might learn something that I didn't know. Now Foo can store a U32 integer or no. Yes, a value storing the cosmic horror of a value not existing. Foo equals null. Yes, but it is a very good construct, but it's probably not good to force every type to be able to be null, which many languages do. Not Sig though, which is incredible. Before we can use the optional value as the non-null type, a U32 integer in this case, we need to guarantee that it isn't null. One way to do this is to threaten it with an or else statement. Okay, I like that. Yeah. Or else is also really nice thing to have. Because as they say, if you have a mutable optional value, if it's null, then you can say or else 2 to make it like the default case or something. Bar will either be equal to the U32 integer value stored in foo, or it will be equal to 2 if your foo was null. Yes. Result equals default. Please threaten the result, so the answer will either be... Okay, so we got the same as before. This will be result or else 42. Yes. And this one has declining quality, but we'll leave this as is. Sorry, that deep thought. Blast from the past. Optional is a lot like error unit types, which can either hold a value or an error. Likewise, the or else statement is like the catch statement used to unwrap a value or supply a default value. Yes. So this is always not, so we should always get 42. Great. Alright. Now we're on to 46. Now to the optional types, we can apply them to structs. The last time we checked in with our elephants, we had to link all three of them together in a circle so that the last tail... Okay, so now we get to this linked list concept here. Where you can have an ending as well. This is because we have no concept of a tail that didn't point to another elephant. Now we also introduced the handy dot question mark shortcut. Const foo equals bar dot question mark is the same as const foo equals bar or else unreachable. Yeah, so it will crash if bar is null, basically. Check out where we use this shortcut below to change control flow based on if an optional value exists. Now let's make those elephants' tails optional. So you add a question mark and see wait, link the elephant so that each tail points to the next. But okay, so should C point to B or I mean A? Link elephants will stop the program entirely. Link elephant doesn't exist. Uncomment to see what happens. Const missing elephant is null. Link elephants. Okay, what will happen? Okay, I have to fix the program first. If E and E2 are valid pointers to elephants, the function links the elephants so that E1's tail points to E2. Yeah, okay. Otherwise it will crash basically here. This function visits all elephants once, starting with the first elephant, following tails to the next elephant. First elephant visited equals true. We print it here. We should stop once we encounter a tail does not point to another elephant. What can we put here to make that happen? Hint we want to so we can use or else and break. That will cause break to be called if tail is null. I wonder if you could put this in a continue expression like this. Now that we've learned about it. Elephants again. Terminated unexpectedly. Okay, well we did this. We did this one. Okay, yeah. So it went to an unreachable place, but I'm surprised it didn't show where the error was. Now it should work. Yes. Okay, so you could do that. You can have the continue expression like this. Okay, very cool. So you basically can do anything in here, I guess. Can you have a... Okay, now we can't test it anymore, but I wonder if you can have like a code block in here, call a function, something, I don't know. Okay, now we're on 47. Help, evil alien creatures have hidden eggs all over Earth and they are starting to hatch. Before you jump into battle, you need to know 3 things. 1. You can attach functions to structs and other type definitions. Yes, now it's a so-called member function. And you can use foo.hello, an instance of foo, and access.hello on that to call this function. Foo says hello. A function, so 2, a function that is a member of a struct is a namespace within that struct and is called by specifying the namespace and then using the dot syntax. Yeah. Okay, so this is like a static member function. It can be called with the type here. I think you can also call this with a member. Maybe you can't actually. Actually, you may have to have a self argument, which we're going to here. The neat feature of these functions is that if their first argument is an instance of the struct or pointed one, then we can use the instance as the namespace instead of the type. So we have a bar type struct here, 3 member functions. They each take so self is the convention to use here, not this or bar. You can name it whatever you want, but the convention is to have self. And yeah, now this is a member function that you can call on an instance like this. So you have an instance here, declare instance here, var bar, and then you can say bar.a, just like in other equivalent constructs in other languages. Notice that the name of the parameter doesn't matter. Some use self, others use lowercase version of the type name, but feel free to use whatever is most appropriate. Yeah, I think the most common is to use self. It's always good to know like the convention and yeah, not have to think about new patterns and stuff. Okay, you're armed. Okay, now please zap the alien structs until they're all gone or the Earth will be doomed. It's like playing a game here. Look at the hideous alien struct. Know your enemy. Okay, we've got alien, we've got health. We hate this method. Hatch. Yes, we hate it. So we will make it work. So this is kind of like a this is kind of like an init function that initialize, or constructor that initializes an instance of alien. And okay, so what do they want me to do? Zap them? I mean, I could just delete them. I guess. Okay, let's leave that for now. Your trusty weapon, zap those aliens. Heat ray, struck damage. We love this method. Zap, alien health. Okay, so we got a point. So we got this pointer to an alien. Alien health is set to be negative equal if. Yeah, and this is also a nice thing about Sig is that sometimes you don't actually need to dereference. It's gonna be implicitly dereferenced for you. And I had a bunch of issues with this in the start because I was used to always have to like explicitly dereference everything. But this is the same thing as this. And yeah, so you don't have to, so this will modify the source here. And there's no, like in C you would use this, I believe, to do the same thing. Here it's all dots. Negative equals if self damage is more than equal to alien health. Wait, if damage is more than alien health, then the alien didn't lose any health. No wait, it loses all health. Oh, if damage is more than it loses. Okay, because it's unsigned, right? So it can't go negative. Otherwise, we do the damage. Okay. So what's happening here? Look at all of these aliens, various strengths. Yes. Let's kill them. Aliens alive, aliens length. Heat ray. Okay, so I have a damage 7 heat ray. Okay. Seems overpowered. We'll keep checking to see if we've killed all the aliens yet. Aliens alive is more than 0. Aliens alive equals to 0. What? Loop through every alien by reference. Yeah. Yeah, so this is also new for this tutorial. So you can, if you have an array and you want to get pointers to each element in a for loop, you have to do it like this. So you have to pass a reference to the array and then put a star here to get the reference to each alien. Zap the alien with a heat ray here. Zap alien dot zap. So we don't have to dereference. We can just call zap directly, and we're zapping with the heat ray. Now does this take no, it's not alien.zap, it's heat ray.zap. There we go. And then we pass the alien here. We can do this because this is a pointer, and that's zaps. Hello Abbreviated, how's it going? Zig tutorials. Well, yeah. The thing is, I realized that I never actually looked through any of these tutorials. I basically picked up things here and there. So I thought that, okay, well, because we looked at ziglings last time, or it came up, and then I thought that, well, why don't I just go through everything, because to cover the bases, because there's some things that I actually didn't know, and I'm putting them in a list here. So these are some of the things that I actually didn't know was in Zig before doing this tutorial. So it does have value. So I didn't know about continue expressions in while loops, where you can have a expression that happens at the end of every iteration, which is very cool. I didn't know in the file writer that you could pass an empty buffer, so you don't even need to define a buffer, which is very nice, because I thought that you had to do that, but you don't. So it's a little bit easier to do that now. Yeah, and some other stuff here. I am not an expert as well, so just so you know. Oh shit. 1 second here. But yeah. Let's see. We're zapping the alien with the heat ray. Yes, we are. If the alien is still above 0, it's still alive. This is a weird... Okay, I guess they're... I would do this the other way around. Like, I wouldn't set this to 0 here and then increase it for everyone that's alive. I would say, I would check if it's 0, then we decrease it. Oops. Because then you don't have to set it to 0. Or am I missing something? Okay, I guess we'll try if it works. Alright, Earth is saved. Yay. Use the heat ray and the method. Terminated unexpectedly. Okay, maybe I missed something with this. Oh, because we're looping through the aliens that already are dead, I guess. Like if... Okay, so we have to put a guard here down. Okay. I guess it's more... Maybe better the other way. I don't know. It doesn't really matter that much. There we go. quick question. You have not checked the animation plugin yet? No, I haven't. I haven't done any animations yet. And this is redundant. Yeah, you could. We could do this then. We could say, but this will cause another loop, though. I think. Because you have to go through it again. Whatever. I mean, you have to do this. Actually, you know what? Continue. I was thinking if you could have an else here to kind of break out, but no. But we're modifying the health here, so yeah, that we can get here. This one will decrease the health. We're zapping the alien. And we're decreasing the health. So over here it might be 0. And we'll do this. Yeah. Alright. 48. Yeah. 48 methods too. Now that we've seen some methods, how methods work, let's see if we can help our elephants out a bit more with some elephant methods. New elephant methods. Okay, we get some tail. We check if we have a tail. Okay. Now this is interesting here. You know, I would change this to just be this. I'm not sure if this is, I mean, and then you can just return this, because then you can, okay, I will show here, because then you don't have to have this function. I guess you can still have this function, but the usage of this will be a bit different here. This links to an offense points to the next, yes. This function visits all elephants once, starting with the first and following tails. Print visit. This gets the next elephant or stops. Which method do we want to use here? If we have a tail, then we get the tail. See, this is I'm gonna show a little bit of refactoring here. Holy what the hell is this? 6 enums also have methods. This comment originally asked if we could find instances of enum methods in the wild. Yeah, the enum methods are also very nice. You can put methods in enums, you can put methods in unions, union enums, which is very nice. Okay, so instead of doing this, like if we have a tail, this is bool, we get the tail or else we break. But since tail is like a nullable, we can just do this, return that, okay? Now, here we just say if we get the tail, we can capture it and just make it the expression here, otherwise break. So now we don't need 2 separate functions to do the same thing. We're grabbing an optional, and in the case where it's not null, we grab the value out and use it. Or else we break. We can also, what you also could do here is you can just do or else here. That's the same thing. So either this is a value, this expression will be that value, or it's null, which means we break. They should put exclamation mark in his name. Yeah. Zap. Alright, that should work, I hope. Yes. Now we're on 49. Trunks and tails are handy things from Holding Hands by Lenore and Link. Now that we have tails all figured out, can you implement trunks? So now we're into doubly linked list or whatever it's called. Alright, so we have tail and trunk. Elephant, tail methods. Get tail. Yeah, whatever. I'm not gonna change this now. And we need trunk methods. I mean, we just... I'll just do this. Go. Is that it? Function is also inverse twice. Tails to trunks. Okay, what's happening? What? Twice? Follow the tails. Okay. Yeah. Gets the tail. So yeah, if they have like, yeah. So if A goes to B in the tail, then B has to go to A in the trunk, right? Because otherwise it would be very strange. Okay, yeah, that works. 50, no value. We live on a placid island of ignorance in the mists of black seas of infinity, and it was not meant that we should voyage far. Yeah, I did get very Lovecraft vibes from that. I think I've heard this before. I never read the books, but yeah. Zig has at least 4 ways of expressing no value. Undefined. No value. 4 ways. Okay. Undefined. Sure. It's like no value for all intents and purposes. Should be thought of value. Should not be thought of value, but as a way of telling the compiler that you're not assigning a value yet. Yeah. If you don't know what it should be at the start, you can use undefined and then set it later. Any type. And I'll show also one thing that I learned here with undefined is that if you set something to undefined and you forget to set it later, the value will be printed, or the compiler in like debug mode will set this to 0xAAAA depending on how large the number is or the value is. So if you have like a pointer, you set a pointer to undefined. I have seen this before, and now I was like, how often does it get like AAAAA? But then now I learned that it's actually a Zig compiler that sets the value to that specific value when you're like developing or running in like development mode. And it's a nice way to catch those cases where you actually didn't set a value of the undefined. Because I've seen so many like seg faults of that address. Okay. Yes, very good. Null, yes, we know about null. Null primitive value is a value that means no value. Yeah. This is typically used with optional types, as with the question mark u8 above. When foo equals null, that's not a value of type u8. It means there is a no value of u8 in foo at all. When foo equals null, that's not a value of type u8. Yes, it's like an either type. It's either null or u8. It means that there is no value of type u8 in foo. I feel like this is so weirdly put. It means there is no value of type u8 in foo at all. Yes, currently it's set to null. I mean, I feel, I don't know. I feel like it's more easy for me to just say it's null. Like, instead of saying it's no value of type U8 in foo at all. I guess it kind of trying to explain what's happening, but I don't know. It's just confusing to me. Foo, because it's very easy to say null is a specific value which has a specific purpose, which is to say it's null, basically, and it's used to say there was an error or something didn't go right or something. There's missing data. And then you have a type that is either null or that or something else. So it's not really that big of a mystery, you know. Error is also, I guess, not a value. So this is kind of weird way of putting it, like these are the things that are not values. But I guess it's kind of like true. Error is kind of like null, except it has a specific kind of like a string message here. Errors are very similar to nulls. They are a value, but they usually indicate that the real value we're looking for does not exist. Instead, you have an error. The example union, error union type of my error U8 means that foo either holds a U8 or an error. There's no value of type U8 in foo when it's set to an error. Yeah, because it's the error now. It's like a union type. Okay. Void var foo void equals yeah, so this is, I guess, I've never actually seen this. Like you could put, you can, well, maybe I have, but I never used it because I never had I never seen the usage of it, like declaring a variable to void and then setting it to this special construct here. Yeah, which you can't really use, I don't think. I guess it's like a way to talk about void in certain circumstances where you might need to have that. I don't know. Void is a type and not a value. Yes. It is the most popular of the 0-bit types. Those types which take up absolutely no space and have only semantic value. When compiled to executable code, 0-bit types generate no code at all. The above example shows a variable foo type void which is assigned the value of an empty expression. Okay, it's much more common to see void as the return type of a function that returns nothing. Yes. Zig has all of these ways of expressing different types of no value. I wish they would show like an example where you could use this. Like, where would this be used? Because I haven't seen one yet, I don't think. Zig has all of these ways of expressing different types of no value because they serve a purpose. Briefly, undefined, there's no value yet. Null, there's no explicit value of no. There is an explicit value of no value. Errors, there is no value because something went wrong. Void, there will never be a value stored here. Please use the correct no value for each question mark to make this program print out the cursed quote from Necronomicon, if you dare. Okay. Is Necronomicon from Lovecraft? I didn't know that. This one is undefined. This one is, I mean, it can also be undefined, I think. It can also be an error. It doesn't matter because it's set here to something else anyway. Note that we need exclamation mark S format for the error union string. Yeah. Print second line. You are a void because you don't return anything. And this one is, I mean, we can set it to null or undefined as well. But it's kind of funny, every one of those could be set to undefined. or null. I mean, I guess it's more correct to set it to null. If you have usually if you have a type like this, you want to initialize it to null. Usually, I mean, it depends on what you want the default value to be, but that's usually how it goes. But here is not the case. I wouldn't say. Well, maybe. I usually don't have values like variables set to error types like this. There's usually like you just call a function and you catch the error directly and handle it. You don't like store it in a variable and do things with it. I don't know. Maybe sometimes I do, but most of the time not. Oh, I forgot a thing. Wait. How is that undefined? You can also do like undefined not that. No. Okay, undefined. There we go. You have to practice these things. That is not dead, which can eternal lie, and with strange aeons even death may die. Okay. 51. If you thought last exercise was deep dive, hold on to your hat, because we are about to descend into the computer's molten core. Shouting down here, the bits and bytes flow from RAM to the CPU like a hot, dense fluid. The forces are incredible, but how does all of this relate to the data in our Zig programs? Let's head back up to the text editor and find out. That's better. Now we can look at some familiar Zig code. Import adds the importer code to your own. In this case, code from the standard library is added to your program and compiled with it. All of this code will be loaded into RAM when it runs. Oh, and I think we name constant. That's a struct. Yes. Remember our old RPG character struct. A struct is really just a convenient way to deal with memory. These fields, gold, health, experience, all are values in a particular size. Add them together and you have a size of a struct as a whole. Yes, because in if you do this in assembly, depending on which flavor you're using, if you're using, I mean, some assemblers have structs, but you know, in assembly, like in the the original, like the instruction set of a computer of a CPU does not have any notion of a struct or what a struct is. So it's basically a purely fictional is the wrong word, but like compiler thing. And basically what you're doing is you're just putting these close together in memory. Anyway, so a struct is really a combination of the memories, fields, values, size. Yes. Here we create a character called a narrator that is a constant immutable instance of a character struct. It is stored in your program as data like the instruction code. It is loaded into RAM when your program runs. The relative location of this data is in memory is hard coded, and neither the address nor the value changes. Yeah. I mean, yeah. So I mean, it kind of depends. I think on how you use it, like because potentially these could just be substituted in certain places in the code where these things are used. They don't necessarily have to end up in read-only memory. Yeah. Anyway, man, I'm nitpicking like a whole lot here. This global wizard character is very similar. The address for this data won't change, but the data itself can, since this is a var and not a const. Global wizard. A function is instruction code at a particular address. Functions parameters in Zig are always immutable. Yeah, they are always constant unless you specify that there should be a pointer, in which case they are mutable. A pointer to a mutable. They are stored in the stack. A stack is a type of data set. Okay, now there's a lot of information here. I mean, yeah. A stack is a type of data structure, and a stack is a specific bit of RAM reserved from your program. The CPU has special support for adding and removing things from the stack, so it is an extremely efficient place for memory storage. Yes. Also, when a function executes, the input arguments are often loaded into the beating heart of the CPU itself in registers. When a function is the input argument is loaded into the beating heart of the... Oh yeah, okay, yeah, the registers. Our main function here has no input parameters, but it will have a stack entry called a frame. Yes, and you would still use... Wait, is that true? You would still use registers. Well, you might not need to use registers when calling a function, but you do. I think you put the return address on the stack or something like that. Here, the glorp character will be allocated on the stack because each instance of glorp is mutable and therefore unique to the invocation of this function. And also I would say like CPUs have like the x86-64 architecture has a function, what's it called? Call instruction and return instruction, which will do those things automatically. Glorp character gold equals 30. The reward XP value is interesting. It's an immutable value, so even though it is local, it can be put in global data and shared between all invocations. But being such a small value, it may also be simply inlined as a literal value in your instruction code where it is used. It's up to the compiler. Yeah, that's what I was talking about. That instead of putting it in read-only memory and then have an address to that memory and read off that, this could just be substituted while compiling into the construction code, instruction code. Now let's circle back to that stat struct we imported at the top. Since it's just a regular zig value, once it's imported we can also assign new names for its fields and declarations. Debug refers to another struct, and print is a public function namespace within that struct. Let's assign standard debug print function to a const name print so we can use this name later. So this is basically like aliasing. It's basically, yeah, it's the same thing. Like you constant set this is an alias for the same function. Now let's look at assigning and pointing values to zig. We'll try 3 different ways of making a new name to access our glorp character and change one of its values. Glorp access 1 is incorrectly named. We ask zig to satisfy memory for now as a character struct. So when we assign glorp to glorp access 1 here, we're actually assigning it to all of the fields to make a copy. 1 second here. All right. Yeah. That's also that. This is very good that they say this, because this is one of the things that I learned very early on and had some problems with arrays specifically. Like if you have a struct with arrays in it, will it actually copy the values of the array? And I still don't know the answer to that question. It feels like sometimes it does, sometimes it doesn't. I don't know. But yeah, so if you have an instance of a struct here called glorp access 1 and we set it to another of that struct. This will actually like expand the code, you could say, and loop through each field and set each field of glorp access 1 equal to the equivalent field of glorp. So it's a really nice, convenient way of copying a struct. Now you have to keep in mind that pointers, of course, will also be copied, but they will point to the same place. So if you modify a pointer, you will modify it the same place as the other one. Print 1, okay, gold equals, okay, yes. Note, if we try to, so this will print false, I guess, since we're changing gold here. If we tried to do this with a const character instead of var, changing the gold field will give us a compiler errors because const values are immutable. Yes. So fields of a const struct are immutable as well. Not just the whole thing, because the whole thing is basically just the sum of its parts. So glorp access 2 will do what we want. It points to the original glorp's address. Also remember that we get one implicit dereference. Yeah, one implicit dereference with struct fields. So accessing the gold field from glorp access 2, just like accessing it from glorp itself. So we have a pointer to glorp now, and then we set gold to 2, which will set the original to 2. Because this is not a copy now, this is a pointer, so, and we automatically dereference. So this is the same thing as doing this, but we don't need to say that. Which confused me at first, but now I'm kind of know intuitively almost how. You basically never dereference it. You never have to dereference things unless you have a pointer to like a primitive value. Then you need to do that. But I usually never have pointers to primitive values. Okay, glorp access 3 is interesting. It's also a pointer, but it's a const. Okay, so this should print true here, since they should point to the same thing. Glorp access 3 is also a pointer, but it's a const. Won't that disallow changing the gold value? It's a pointer, but it's a const. Well, no, it's a so you can't change the location of, or the where it points to is what you can't change now when it's a const like this. And this also tripped me up at the beginning, like, because you're thinking like, oh, I'm seeing const here, so the contents can't change, but they can. If you point to a mutable, you can. So you have to put const here for it to be immutable. the contents equals that, and then we still can change it, but we cannot change this. We cannot change this to glorp access 2, for example. That's not possible. Okay, and this should be true as well. Note, if you try to do this with a const character pointer, that would not work, and we would get a compiler because the value becomes immutable. Yes, that's what I was saying. Moving along, when arguments are passed to a function, they are always pass the constants within the function, regardless of how they were declared in the calling function. Yes, that is true. You can't do this. You have to make a copy if you want to do anything with that bar. But in this case, you're defining a local variable, which is fine. Knowing this, we see if you can make a level up work as expected. It should add the specified amount to the supply character's experience points. Fix 1 of 2 goes here. Okay, so glorp levels up with reward. except this is a, you know, a local. So we have to do this in order for it to be mutated, and then here we have to take a pointer in order for that to work. Otherwise you're just modifying a local copy in here, and the changes will never be seen anywhere else. Okay, and there's more. Data segments are located at compile time, and the stack allocated at runtime aren't the only places where the program data can be stored in memory. So what we have, the heap. Data segments can be like read-only, can be read-write. That's like part of the program when it's like loaded up. It's part of the program data, like the executable file. The stack. There's also, I think there's also like ways to generate data, so you don't have to store everything like straight up. Like generate a bunch of zeros to have space for things, but you don't need to store every zero in the actual executable. The stack and the heap. So now we're getting to allocators, I think. There aren't the only places where programs stored in memory. They're just the most efficient. Sometimes we don't know how much memory our memory will need until the program is running. Also, there is a limit to the size of the stack memory allowed to the program, often set by operating system. For these occasions, we have the heap. I actually tested this, so I think I have like 4 kilobytes. No, it was like 4 megabytes or something like that. 4 megabytes was the limit of the stack for me. You can use as much heap memory as you like within physical limitations, of course, but it's much less efficient to manage because there is no built-in CPU support for adding or removing items as what we have with the stack. Also, depending on the type of allocation, your program may have to do expensive work to manage the use of heap memory. We'll learn about heap allocators later. Phew! This has been a lot of information. You'll be pleased to know that the next exercise gets us back to learning Zig language features so we can use it on a way to do more things. Okay, cool. So are we done here? Yes. Now we're on to slices. We've seen passing arrays around could be awkward. Perhaps you remember a particularly horrendous function definition from quiz 3. No. This function can only take arrays that are exactly 4 items long. Print powers of 2 numbers. Okay. That's the trouble with arrays. Their size is part of the data type and must be hard-coded into every usage of that type. This digits array is a 10 U8 forever and ever. Yes. Thankfully, Zig has slices, which is awesome, which let you dynamically point to a start item and provide a length. Here are slices of a digit array. So basically a slice is just a pointer with length. And it has safety and types and everything nice with it, and also some flavors as well. As you can see, so we have foo equals digits 0 to 1, so that's actually just one element starting at 0 and goes to 1 exclusively. So you could put 0, 0 in here, which means it has no elements. Or 0, 1 means 1 element, and so on. Yeah. And then 0, point means you just grab everything. As you can see, a slice x to y starts with the index of the first item and the last item at y minus 1. You can leave the y off to get the rest of the items. The type of a slice of an array on an array is U8. Array of U8 item is slice of U8. Yeah, so slice. So basically, you don't put anything in the brackets to make it a slice. Well, that's not entirely true, but it's true in this case. Cards. Okay, so now we're playing cards. Please put the first 4 cards in hand 1 and rest hand 2. Hand 1. The first 4 cards, so that would be that. There would be 0, 1, 2, 3. And then 4 to the rest. Okay, we'll print hand. This one takes a slice of U8, which is really nice because now you don't need to know the length of this. It's kind of like an array, but it's it's a slice. It's an array with dynamic length. Well, it's not really dynamic. It's more like, well, I guess the type in type land it's dynamic, but it's like, yeah, it can be any length. But a slice, you can't change. Well, can you change the length of a slice? No, I think you just reassign it in that case. Anyway. Now you get a hand here. We don't know the length, but it is runtime known, so we can loop through it like this. Okay, and to get the length, you say hand of length. You can get the length like this, and you can even get the pointer, the backing pointer, here. I think I'm not sure if this pointer is actually this pointer has to be like offset with where it starts. So this is not like, you can't get the original pointer guaranteed with this, because the slice can start at anywhere along the original pointer. Under the hood, slice is stored as a pointer to the first item and a length of the slice. I think, yeah, it has to be of the slice, right? Otherwise you can't know where it starts. Then you would need more data. Okay. That worked. Slices 53. You are perhaps tempted to try slices on strings. They are arrays of UA characters after all, right? Slices on strings work great. There's just one catch. Don't forget the sig strings literals are immutable values. So we need to change the type of slice from this to const this, yes. See if you can fix this zero wing inspired phrase. The scrambler. Okay, great. Okay, great base for all your justice are belong to us. What the hell is happening here? Do I have to count? Print phrase. Well, okay, let's see what's going on here. Okay, I think they just put the things in there for us, maybe. What do I need to fix? Let's see what the result is. Oh, expected. So it's just a type error here. So these needs to be const. Whoops. That the only issue? 53. No. And then you should take const as well. Doesn't make sense if we don't want to modify it anyway, so there we go. All your base belong to us for great justice. 54. You can also make pointers to multiple items without using a slice. Yeah, so that's the array, and then we have a slice of everything. We have a pointer. So this, yeah, I never used this. It's kind of like a pointer, but it has multiple items. Potentially, because you could point to the last item and then you only have one item. But okay. Foo slice from pointer, and you can also slice from existing pointers as well. This is kind of interesting. Feels very unsafe though, because this kind of pointer it doesn't have a length, so we don't know how long it is. So if you do this, you don't get compiler security to know if you're out of bounds or not. I'm pretty sure that's how it works. The difference between foo slice and foo pointer is that the slice has a known length, a pointer doesn't. It is up to you to keep track of the number of U8s foo pointers points to. Yeah. Take a good look at the array type to which we're coercing the Zen 12 string. The real nature of strings will be revealed when we've learned some additional features. Yeah, the real nature of strings. Okay. So we have a constant array of, or wait, we have pointer to a const array with mutable values. This is kind of strange because if you have a constant array, that means that the things inside are also constant. Okay, memory is a resource. It will also have been valid to coerce. Like, can you coerce to a slice? No. So okay. Okay, this is kind of strange. This is where I feel like this is weird because usually you do this. This is the type of an array of constant U8s. But when you have a pointer here, it's the other way around. Or what? Or maybe it's okay. I'm just lying here. No, it's because if it's a slice, you do this. Yeah. You can have a constant slice. It's kind of like a constant pointer to a constant unit. Okay. But if it's an array, you say const. Now it's a constant array. Now it's a mutable array. Now it's a pointer to a constant array. Okay. Yeah, it's kind of, to me it just feels a little bit inconsistent, but I don't know. It would have been valid to coerce to a slice. Now let's turn this into a many item pointer, which is this one here. And so it's a many item pointer to immutable values. Okay, so we're so I think this is like implicitly coerced, or not coerced really, it's more I mean, it's basically under the hood. I think this is the same thing, like it's just a pointer. Actually no, because this has a length as well. So this is the pointer part. It's kind of like doing this. No, it doesn't have a pointer. Do we do this? I don't know. Anyway, it's okay to access send many pointer just like an array or slice as long as you keep track of the length yourself. A string in zig is a pointer to an array of const U8 values or a slice of const U8 values as we saw above. So we could treat a many item pointer of const U8 as a string as long as we can convert it into a slice. Hint, we do know the length. Please fix this line so the print statement below can fix it. Yeah, so we can't do this because we don't know the length. Zen. Hello Blue, how's it going? So we have to say whatever thing is here. I guess we could say Zen 21 dot length, because it will be implicitly dereferenced. No? Wait, did I say wrong thing? Oh, Zen 12 dot length. Okay, that was it. Now what's up here? All of these pointer types starting to get confusing? Yes. Free zig pointer cheat sheet using U8 as the example type. 1 U8 pointer to 1 U8. 2 U8s pointer to many U8s potentially. or unknown number of U8. Yeah, it could be 0 as well. Could be 1, could be many. And this is same but immutables. This is a pointer to an array of 2 mutable U8s. This is a pointer to a constant array of 2 U8s. This is a slice of U8. This is a slice of mutable, slice of constants. Okay. Alright, let's go on here. A union lets you store different types and sizes of data at the same memory address. How is this even possible? The compiler sets aside enough memory for the largest thing you might want to store. And then you have to keep track of yourself on what it actually is. In this example, an instance of foo always takes up U64 space in memory, even if you're currently storing a U8. So unions always felt weird to me, like when I first encountered them in C or C++ or whatever. Because it felt like, okay, since you had to keep track of, like, you have to sort of know which type it is yourself in the code. You can't, like, know what it is unless you have another variable that tells you what it is. But, so I always had trouble in kind of figuring out, okay, where should I use this and why? The syntax looks just like a struct, but a foo can only hold a small or medium or a large value. Once a field becomes active, the other inactive fields cannot be accessed. To change active fields, assign a whole new instance. Yeah. So the compiler knows here, but I mean, if you have a function that takes this type, you have no idea which one it is unless you kind of assume that it's one of the types. So it's like to me it kind of defeats the purpose. I don't know. I still have trouble. You know, I never really studied it a lot, but it was just like my initial thought about this. But we'll get to something that can be used later, which is basically everything used everywhere for me. Once a field becomes active, or inactive, it can be accessed. To change fields, assign a whole new instance. Yes. Unions can save space in memory because they let you reuse a space in memory. Oh, I see. It's for saving memory. Sure. So it's kind of a way of tricking the stack to reuse it again or something, I guess. Okay. They also provide a sort of primitive polymorphism. Yeah, very primitive. Here, foobar can take a foo no matter what size of unsigned integer it holds. Foobar f foo boy, yes. Oh, but how does foobar know which field is active? Zig has a neat way of keeping track, but for now we'll just have to do it manually. Well, I don't think it has a way to keep track of it if it's just a straight up union. Tagged unions, however, that's another thing. But for this one, I don't think it can keep track of it. You have to sort of assume which one it is. We just started writing a simple ecosystem simulation. Insects will be represented by either bees or ants. Bees store the number of flowers they're visited that day, and ants just store whether or not they're still alive. Okay, so insect is a union of flower visited or still alive. So it can either be like an insect, or I mean an ant or a bee, I guess. Since we need to specify the type of insects, we'll use an enum, ant or bee. A or B, yes. We'll just make one bee and one ant to test them out. Okay, and then we'll print insect report. Oops, we made a mistake here. Print insect ant should be Ent or B A, enter B C. Okay, I see what you're doing here. You're passing, yeah, this is what I said, like you're passing along instructions on how to use this union. So are we actually saving space here? I mean, I guess it depends on this, on the size of the things, but yeah. Okay, I guess technically you could have, if these are like big structs and you want to reuse that memory, and then you pass along a small like byte to know which one it is, then you can save memory, or I guess like, yeah, 64 bits minimum or something, or maximum. Eccentric Dr. Zoraptera says that we can only use one function to print our insects. Dr. Z is small and sometimes inscrutable, but we do not question her. So we're getting the insect, but we need to know what insect it is, so we need to pass this along, and we're switching if it's an A. So we also need to trust that we're getting the correct thing here. Ant alive is this, and bee visited, so this one. Insect report, ant is alive is true, bee visited 15 flowers. Great. 56. It's really quite inconvenient having to manually keep track of the active field in our unit. I think also the only reason for having the other, like the original union, is because of, well, I guess for one, some people might know some neat tricks with that to make it more efficient, I guess. But another thing is also like importing C libraries and C types. Then C has these unions, so Zig also has those unions to make it convenient. It's kind of weird that you have to have like a mirror of another language's like constructs in your language just to make the integration work. Like it feels a little bit limiting maybe, or it kind of bloats the language with stuff that you might didn't want to have there. But I guess it does fill a purpose, you know. Anyway, you don't have to use it if you don't want to. It is really quite inconvenient to manually keep track of the active field in our union, isn't it? Yes, it is very inconvenient. Thankfully, Zig also has tagged unions, which allows us to store an enum value written within our union representing which field is active. Yes, so here's an enum, and it has small, medium, large, and then you can make a union, a tagged union, that has the same fields. The fields has to be the same as the enum names here, small, medium, large. And now all of a sudden we don't have to have a separate value to keep track of which value this is. Now we can use a switch directly on the union to act on the active field. F equals foo, small equals 10, and then we can switch on F. Yeah, this is very convenient here. So we switch on F. F is a union enum type, or a union tagged union type, and we can switch on it, and we can have these cases, which is the union, or I mean the enum values, the cases here, and we can also even grab out, we can capture the value itself and then do something with that value. This is a really good pattern that I'm using all the time. And I also realized that, okay, in the original, you know, in defense of the original unions, like if you have a tag, you can make it, you know, a manual tagged union and use it that way. So in a language where you don't have tagged unions built into the language, you can still make tagged unions manually. So yeah, I realize now that that's a good thing, but it's not type safe. It's not, you know, it's error prone as well, because you can mistakenly get like there's no checks for, the compiler cannot check like if it's correct, unless maybe you have like a linter that could sort of construct out of comments or out of the structure and something like that maybe. But yeah. Anyway, let's make our insects use a tagged union, because I know that C has a lot of, or C++ and C has like yeah, you can use linters and stuff to improve things a lot. Insect stat. Flowers, yes. And you don't actually have to do this. This is a nice way to make this named, this enum here, but you can just say enum like this, and it will like implicitly create an enum for us. If we don't really need to use this enum here, if we don't need to have this enum, we can just put this here, because usually you actually don't need that, and that will still work the same. It's basically the same thing, except we're not naming the enum, and we don't have to specify these things multiple times, like flowers visited still alive. So now we just need to do this one time and it's done. Could it really be just as simple as passing the union and B, and then we switch on the input. Yes. That should work. By the way, did unions remind you of optional values and errors? Somewhat, maybe. Optional values are basically null unions and errors. Oh, I see. Yeah, okay. I mean, you can't if on a union, but you can. Can you switch on a null or error union? Yes, you can switch on an error, you can. But you can't switch on a... You cannot switch... I mean, I wouldn't call them super... I mean, in case of how you're like using them in the code, like which keywords you're using, they're very different than the structure around it. Now we can add our unions to the mix to handle whatever situations we might encounter. Union tag. I mean, really, I was gonna draw a parallel with Haskell, but I'm not gonna do that. Now we can add our unions to the mix and whatever structure kind of union tag. Yeah, so the good thing about this, the very good thing about this is, well, flowers visited, we can also like change this. Let's like I would have this called a B, and then have a struct here, and then flowers visited like this instead, and then ant still alive, because then it's kind of more descriptive of what's going on here. And then you are flowers visited 16. Now you have to say it like this, but you can make convenience functions to initialize them as well if you want. But, and then ant equals still alive true, or what was it? Was it true? Yes. And then we can add now, and now this would be ant. You would do this, and if you want to add another insect, you do that. Okay, the only thing I can think of is a gråsugga, which is like ancient insect. Okay, cockroach maybe. I don't know. And this will be feet stomps evaded. Okay. Feet stomps, foot stomps, I don't know. And then we have this guy, 32, very evasive. Okay, but the good thing here now is that you get, well, you get unused constant here, but if I put this here, now we should get, okay, I don't get it in the thing here, but I should get it here. Switch must handle all possibilities. Yeah, the same thing as I showed before. Now you have to implement this, otherwise the compiler is gonna complain. But it forces you to do this. Yeah. So now we just need to remove that to there we go. All right, 57. I'm just gonna refill my coffee. I'll be right back. With 10 unions, it gets even better. If you don't have a need for a separate enum, you can define an inferred enum with all your unions all in one place. Just use the enum keyword in place of the tag type. Calls true equals union enum. Small, medium, large. Let's convert insect. Dr. Zora Petter has already deleted the explicit insect stat enum for you. Okay. Great. Question mark. Inferred enums are great, representing the tip of the iceberg of the relationship between enums and unions. You can actually coerce a union to an enum, which gives you the active field from the union as an enum. Yeah. So you get an enum value from a union, which is the, yeah. Okay, I did know that. What's even wilder is that you can coerce an enum to a union, but don't get too excited. That only works when the union type is one of those weird 0-bit types like void. Yes, you can have a thing here, no value, like this. And then you can coerce an enum to that. It's basically just an enum value, except it doesn't hold a value. I wonder if you have, let's say you have insect enum, and you have these things, right? But then you assign this to something. If you get the union if you coerce this, okay, and then this would be, I'm guessing you would get 16 if you coerce this to an enum. You would get 16. Okay. Tagged unions as most ideas in computer science have a long history going back to the 60s. However, they are only recently becoming mainstream, particularly in system level programming languages. You might also have seen them called variants, subtypes, or even enums. Sometimes I've seen variants. I'm thinking about Haskell. I think Haskell has something called subtypes, but they are like you put like you have my I don't know what to call this. Okay, well, insect. I think you have to say data or new type, and then and or b. I think this is called a sum type. No, you don't have. You don't have these semicolons. I think this is a subtype, and I think this is kind of like a tagged union. I think, yeah, because we can pattern match on which of them there it is later. So this has to encode the type into, like, which one it is into the data itself. So this, I think this is kind of exactly like our tagged unions here. All right. Okay, now we're on to 58. We've absorbed a lot of information about the variation types we can use in Zig. Roughly in order, we have single item pointer, slice, array of 5 U8s, many item pointer, set of unique values A and B, set of error unique error values E and F, group of values Y and Z, single value either U8 or I32. Values of any of the above types can be assigned as var or const to allow or disallow changes mutability via the assigned name. I always thought that the union was kind of weird name, because union in like set theory means you take multiple things and put them in the same set. Although every set needs to be unique, but you kind of group things together, which to me feels more like a struct. This is more like I don't know. I mean, it doesn't really have. I guess maybe it doesn't really have a neat conversion to set theory. I'm not sure actually. I don't know too much about it, but I know that a union is like a grouping. So that I always thought that was kind of a weird name for this, because it's an either type. And even I think in TypeScript they call, if you have like type A equals B or C, this is called a union type, but D equals E and F, this is called an intersection type, I'm pretty sure, which was always weird to me. Like, how can this be an intersection? You're joining the two types together, so that should be like a union. It's like the other way around. This is like it's either B or C. This is E and F. Yeah. Anyway. Values of any of the above value types can be assigned var or cons to allow or disallow changes within the various assigned name or so-called identifier. Yes, we can also make error unions or optional types from any of the above. Yes. Knowing all of this, maybe we can help out a local hermit. He made a little zig program to help him plan his trips through the woods, but it has some mistakes. A note about this exercise: you do not have to read and understand every bit of this program. This is a very big example. Feel free to skim through it and then just focus on the few parts that are actually broken. Okay. The gruel is a nod to Zork. Yes, the classic adventure game, text adventure game. Trip error, unreachable. Let's start with places on the map. Each has a name and distance to difficulty to travel, judged by the hermit. Note that we declare the places as mutable because we need to assign the paths later. Interesting. Why is that? Because paths contain ports to places and assigning now create the dependency loop. Ah, I see. Unnecessary evil. Yeah, this is a type. This is... And then we have a bunch of places that are mutable. I mean, I guess you could make them mutable first and then make a list of immutable places and use that from now on. Oh, cool. A hermit's hand-drawn ASCII map. Archer's Point. A river. A bridge. A forest, I guess, or yeah, it's called a grove, so I guess cottage, a boat, a pond, the east pond, and a waterfall. So we're going down, and then we have the fox pond. Interesting. So I guess we start out at the cottage, maybe. We'll be reserving memory in our program based on a number of places on the map. Note that we do not have to specify the type of this value because we don't actually use it in our program once it's compiled. Don't worry if this doesn't make sense yet. It sort of doesn't make sense. Now let's create all of the paths between sites. A path goes from one place to another and has a distance. Alright, so from and to... Oh, so we're specifying from as well. From and to, and then distance. Yeah, okay. By the way, if the following code seems like a lot of tedious manual labor, you're right. One of the Zig kill features is letting us write code that runs at compile time to automate repetitive code, much like macros in other languages. But we haven't learned how to do that yet. Too bad. So we have a path from Archer Points to bridge, distance 2. From bridge to Archer Point, distance 2. From bridge to Dogwood. Okay. Yes. A lot of paths. Once we plotted the best course through the woods, we'll make a trip out of it. A trip is a series of places connected by paths. We use a trip item union to allow both places and paths to be in the same array. That's cool. Trip item, place and path. This is a little helpful function to print the two types of items correctly. Print me switch. Oops, the hermit forgot how to capture the union values in a switch statement. Please capture each value as P so the print statements work. Oh no. There we go. The hermit's notebook is where all the magic happens. A notebook entry is a place discovered on a map along with the path taken to get there and the distance to reach it from the start point. If we find a better path to reach a place, shorter distance, we update the entry. Entries also serve as to-do lists, which is how we keep track of which paths we explore next. Cool, so we got place coming from, we have path and distance to reach. Alright. Okay, yeah, so we're like, okay, so we're saving sort of a history of what we're doing. So we're at the place archers points. We start at archer points and we take 2 distance to go to bridge from archer points. I mean, we really don't need from if we have an history. We could just look at the previous entry then. And the distance can also be looked up from... Okay, well, whatever. End of entries, okay. Hermes Notebook. Remember the array of repetition operator star. It is no mere novelty. It's also a great way of assigning multiple items in an array without having to list them one by one. Here we use it to initialize an array with null values. Yes. Very good. So we have an array, which means we don't need an allocator to place it. We place it on the stack instead. And with place count, how much is this? 6? Okay, I mean, we are using this as a length of this array. Anyway, the next entry keeps track of where we are in our to-do list. Next entry, mark the start of empty space in the entries. We'll often find to an entry by place, if not one found, return null, get entry, return null. So entry by place. Oh, I see. All right. Right, so we're just looking up the entry by place here. If we're at the end of our entries, we break. Here's where Hermit got stuck. We need to return an optional pointer to a notebook entry. What we have with entry is the opposite, a pointer to an optional notebook entry. To get one from the other, we need to dereference entry with dot star and get the null value from that with optional with dot question mark and return the address of that. If the if statement provides some clues about how the dereference and optional value unwrapped look together. Remember that you return the address with the AND operator. Try to make your answer this long. What? To get from one of that, what is the dereference and get the null value? And return the address of that. The if statement provides some clues about how the dereference is optional. Oh, okay. We need to dereference entry. Wait, what? But, okay, if the place is equal to entry place, we return the entry. Oh, they're talking about over here. Okay. Entry. I mean, yeah. Also, I think you can do like if you can do like place, entry place equals entry question mark. You can do this directly because it's like dereferencing automatically, so you can do like or else. I'm pretty sure, or else we wait, or else we wanna continue, I guess. Yeah. And then if entry place is equal to place, we return entry place. But now this is no longer a pointer, I guess. So we have to now. Okay. I guess it's kind of a weird thing. I usually don't have that. Okay, whatever. Let's continue. The check note method is a beating heart of the magical notebook. Given a new note in the form of a notebook entry struct, we check to see if you already have an entry for a notes place. If we don't, we'll add the entry to the end of the notebook along with the path taken and distance. If we do, we check to see if the path is better, shortened distance than the one we noted before. If it is, we overwrite the old entry with the new one. Is this a pathing, like finding the shortest path algorithm? I missed, or I must have forgotten what we're doing here. Okay, so we're checking. So we're getting the entry if we have already visited this place. If we didn't, we just add a new entry. If we did visit this place and the distance was shorter this time, we rewrite that entry with this note. Okay, interesting. So we're basically finding all the shortest routes to every other place, or to every place from, I guess, one other place. The next two methods allow us to use the notebook as a to-do list. Has next entry, get next entry. Okay, increment after getting entry. Yes. After we've completed our search of map, we'll have computed the shortest path to every place. Okay. To collect the complete trip from start to destination, we need to walk backwards from the destination's notebook entry, following the coming from pointer back to the start. What we end up with is an array of trip items with our trip in reverse order. We need to take the trip array as a parameter because we want the main function to own the array memory. What do you suppose could happen if we allocated the array in this function's stack frame, the space allocated for the function's local data, and return a pointer or slice to it? What would happen is that it's not guaranteed that that data will stay the same because it's going to be occupied by other function calls and possibly modified, very much likely. So it's an unstable area of memory. Looks like the hermit forgot something in the return value of this function. What could that be? The return value. It's void. Oh, I see. It's an error union. I guess this could be a trip error. So we start at the destination. This function needs to return an error if the requested destination was never reached. This can't actually happen in our map since every place is reachable every other place. Right, I was thinking about that, but pretty sure they made sure that that was the case. Cool. Variables hold the entry we're currently examining and an index to keep track of where we are appending trip items. Current entry is at the end of each looping continue expression increments our index. Can you see why we need to increment by 2? So we are populating a trip now from end to start, I think. So trip I equals to trip item. Yeah, because we're doing this. The current place, an entry coming from nowhere means we've reached the start, so we're done, right? Otherwise, entries have a path. So we're populating +1 with the next path. Now we follow the entry we're coming from. If we weren't able to find the entry we're coming from by a place, something has gone horribly wrong with our program. This really shouldn't ever happen. Have you checked for grooves? You don't need to fix anything here. Okay. Previous entry is get entry coming from previous. No. Yeah, because we're didn't we already check that here though? I don't understand this. Oh, get entry. Wait, but what type is this? This is a place. Oh, I see. So it's like if you have a place, yeah, it's like something went wrong in the register before. And then we get eaten by a groove, which shouldn't happen. Main, here's where the hermit decides it would like to go. Once you have get the program, we can try some different places on the map. Start a destination F. Store each path as array as a slice in each place. As mentioned above, we need to delay. Make these references to avoid creating that dependency loop when the compiler is trying to figure out the allocate space for each item. Now we create an instance of the notebook and add the first start entry. Note that no values. Read the comments for the check note method above to see how this entry gets added to the notebook. Notebook. Well, I've read everything so far, so I don't need to do that. Get the next entry from the notebook, the first being start entry we just added, until we run out, at which point we'll have checked every reachable place. Great. For every path that leads from the current place, create a new note. Yes. Once the loop above is complete, we calculate shorter paths. Side memory. Okay, so we're basically, yeah, we're because trip was like 2 entries for each place, I guess, like the place and the path, and then yeah, so we need to take place count times 2. We don't have like, yeah, okay, so he's trying to visit every place at least once, I guess. Or this is like the maximum. You're never visiting the same place twice. Get trip to error. Oh no. Print the trip with the help function. Oh, okay. Remember the trips will be and trip items contain place or path from destination to start. Remember the space in the trip array will contain no values. We need to loop through items in reverse, skipping those until we reach destination from the array. We convert the U size, length of the user. Yes. Going deeper. In computer science terms, our map places are nodes or vertices. The paths are edges. Together they form a weighted directed graph. I mean, I would call this more like math terms, but yeah. I guess it's like computer science kind of hijacked these definitions. It is weighted because each path has a distance, also known as a cost. It is directed because each path goes from one place to another place. Undirected graphs allow you to travel on an edge in either direction. Yeah, so this is like graph theory. What's it called? Like, yeah, graph theory, I think. Since we append new notebook entries at the end of the list and then explore each sequentially from the beginning like a to-do list, we are treating the notebook as first in, first out queue. Okay, so we're talking about like how, because I didn't really get the whole thing. I mean, I know, but I know kind of the purpose of the program, but not kind of like exactly how they managed to actually tie the knot here. So new notebook as an end of the list and explore each sequentially from the beginning like a to-do list. We are treating the notebook as first in, first out queue. What do you mean first out? We're just adding things and then we are also replacing things, right? When are we removing things? Okay, I don't know. Or maybe when we are making the trip array or something. Since we can okay, yeah, because we start at the start appending, and then when we're done, we're doing like we're popping things off at the end there. So it's kind of like a stack. It's just like a stack. Since we examine all closest paths before trying further ones, thanks to the to-do queue, we are performing a breadth first search. Right. In contrast to a depth first search. By tracking lowest cost path, we can also say that we're performing a least cost search. Right, the whole point of the algorithm is to find the least cost path or trip. Even more specifically, the Hermit's notebook most closely resembles the shortest path faster algorithm, attributed Edward F. Moore. By replacing our simple FIFO queue with a priority queue, we would basically have Dijkstra's algorithm. Priority queue retrieves items sorted by weight. In our case, it would keep the paths with the shortest distance in front of the queue. Dijkstra's algorithm is more efficient because longer paths can be eliminated more quickly working out on paper. No, I won't do that. But very nice. I didn't actually know about the shortest path faster algorithm. I've done Dijkstra's algorithm a couple of times, but yeah. Okay, so that's good. So the fastest is Archer's Point Bridge, Dogwood Grove Cottage, East Pond, Fox Pond. Okay, and now we're on to 59. So we only got what, 61 left? No, 51 left. So we're like halfway through. Okay, I'll just try to make this a bit faster here. Ziglings to express integer literals in several convenient formats is all the same value. Oh, I actually didn't know about octal, but I mean, I never use that, so it's not really that important for me. Unicode, I knew that it existed, but I basically never used this. You can also place underscores. Yeah, I know about that. That's really nice when working with colors. You can have red is FF000000. Yeah. Please fix the message. Do I have to look up these values? I mean, I could say zig and then we'll print this as I think D, or can you do like O for octal? No, you can do X for hex, and then we can work it out. So we have like 5A, 6, 9, 6, 7, 5A. So this is like half of hex. 5. So I guess this should be 5 as. No, wait. 5 means like 5 times 16, which is equivalent to 5 times 8 times 2, so it should be 10. So this should be A, right? No. Wait, it only goes to. Wait, it only goes to 8 or 7. Okay. Wait, how much is this? 0. $59, $59. I'm confused. Wait, so this is 2 or 8 to 0, 8 to 1, 8 to 2. And this is like 16 to 0, 16 to 1. Because the thing is, like, hex is like this. Oh, you can't have multiple. So the first 6 here is like the 4 things here. Actually, it's 4 things here and then 1 thing there. So you have to can sort of take 4 things there and turn it directly into 1 hex. And here you take 4 things here and turn it directly into 1 hex. Into this one. So this 4 is 2 to the power of 4, which is 16. Okay, but how would so can you turn 8 to the power of 2 is 60? Wait, 64? 16 to the power of 2 is, I think it's like 256. Yeah, because this is 1 byte, so this would be 256. Okay, so it doesn't really line up, which was what I was thinking first, like we could line it up and convert it. But basically 5A in hex is gonna be, so 5 is 4 plus 1, and then A is 10. And then the octal version. I'm doing good, Blue. How are you doing? I'm just chilling, doing ziglings, some programming. 0. Oh, yeah, this is weird. I mean, okay, maybe it's easier to put it in decimal. Let's do decimal first. So A is 10 plus 5, which is 5 times 16. So that will be 50 plus 30, so 80, so 90. So this is 90. And now we turn this into octal. 90. Wait, is this even good? So 64. So 164 fits there. No, wait, we've got 1. Yeah, 8, and then 64 is over here. Okay, 64. Now we got 64. 90 minus 64 is 26. So how many 8s fit in 26? It's gonna be 24. That's 3. 2. So 2. Okay. Yes, that's correct. Okay. Okay, next one we have actually we can just put B in here, I think. Maybe. No. We can't. So we got 69 is the next one. So that should be easy. We got 4 plus 2, that's 6. 9 is this minus 1. It's 8 plus 1. Okay, and then the last one is just 67. There we go. Okay, I don't. Okay, that was a bit weird. Like, you had to. It's like the first one where you have to do things. It feels like you had to do like things outside of the code to figure it out. But it's fine. I don't know. Maybe I just missed a huge hint here. I mean, it's kind of like a Caesar. What's called a Caesar cryptography. Like you just increase. Like you see, the letters were maybe the same. Maybe there was like 2 off or 1 off every time. And you had to just adjust it depending on the thing. We're doing good, great. What are you up to? Are you learning Zig? Okay, now we're on floats. Zig has support for IEEE 754 floating point numbers in these specific sizes: F16, F32, F64, F80, and F128. Very cool. Floating point literals may be written in the same ways as integers, but also in scientific notation. Oh, I didn't know about that. Well, I will not have a use for it, but that's cool. Well, I won't have a use for it maybe in my current project, but maybe in the future. Hello 0341. Why do programmers always confuse Halloween with Christmas? Because October 31 equals this. Linking back to the octal and decimal conversion. Good one. Welcome. How's it going? I guess happy Halloween you could say now, maybe. Hex floats can't use the letter E because that's a hex digit, so we can use a P instead. What? Oh, I see. Because reasons? Why P? Why E actually? I mean E for exponential or something. I don't know. P for exp. I don't know. Maybe it looked weird with x, 2 x's. Be sure to use a float type that is large enough to store your value, both in terms of significant digits and scale. Rounding may or may not be okay, but numbers which are too large or too small become infinite or negative infinite, positive or negative infinity. Yeah, this is actually interesting. Like, I don't know how they, because like positive and negative infinity, somehow they encode that in, like in Zig, they encode infinity in the number. Maybe it's like the max and min values, because otherwise they would have to take space out of the floating point number to mark it as infinite. Yeah, no, but yeah, I guess it's kind of the same thing, because you can't really use the last value. I guess nothing is larger than the last value anyway, so it kind of checks out. Except if you want to take that number and modify it. Do we have, like, is it special modification then for floats? Like if it's infinity and you do -5, it should still be infinity in maths. Okay, here I guess they say there. Okay, when performing math operations, numeric and literals, ensure the types match. Sig do not perform unsafe queries behind your back. Yeah, I know. Okay, F16 is 5, no error. U16 is 5, literal of a different type. What? It's a. I mean, what do you mean? We don't know the type. It can be multiple types. Okay, whatever. Bar F16 foo is an error. Yes. Sadly, well, I guess it is good, but it's just sometimes you have to do a whole bunch of casting and it's a pain. But yeah, you do learn how to, you know, optimize around that, I guess. Please fix the 2 float problems with this program and display the result as a whole number. Okay. The approximate weight of the space shuttle upon liftoff, including boosters and fuel tank, was 4,480,000 pounds. We'll convert this weight from pounds to metric units at a conversion of 0.453592 kilograms to the pound. Okay. This is a weird way of doing things. Okay, I guess this like puts 3 zeros in here. And then that looks correct. By default, float values are formatted in scientific notation. Try experimenting with D and D colon 0.3 to 6. Okay, well I know how it works, so D just means it's gonna be floating point without any or with maximum precision. And then you can add dot whatever. 0 means 0 decimals. 3 means 3 decimals. What do I actually have to fix? Please fix the 2 float problems. Oh, is it because it's small enough? Did it say F16 can be... 23? I mean... This doesn't come close to that. In fact, this will be like 400,000 something, or 1 million, or maybe 2 million, 2.5 million or something. The only thing I'm thinking of here is like, this is a comp time float, this is a comp time int, so you would have to put like 0.0 here to make it a point time float. Infinite tons. Okay, wait, am I missing something here? Do you have to be larger here? Is this just... wait, 4 million. Point this to the pound. What? Wait, what am I missing here? Oh, tons. Oh, this is kilograms. Okay. Ugh. I mean, okay. We could put a dot there, or just remove this, I guess. Okay. Yeah. Okay. There we go. It'll only take us a moment to learn the zig type coercion rules because they're quite logical. Types can always be made more restricted. Foo is U8 equals 5. Pointer to U8 is foo. Pointer to const U8 is P1. Mutable to immutable. Yeah, okay. So that counts as more restrictive of what you can do with it. Numeric types can coerce to larger types. U8, U16, 5 because yeah, okay, cool. So now we kind of learned this because I never went through the actual rules for this. So yeah, you can go to larger types if you have like the same type. And single type pointers also coerce slices and many type pointers. I see. So you have an array 3, you have a slice that is, oh, I didn't know you can do this, like just take the address of array. I thought you always had to do this, but you can just do this. I guess that would be the same thing since we know that this is an array and that this can be set to an array. Single item pointers, but there's no single item pointers here. This isn't a single, this is a many type pointer. Okay, whatever. Single item mutable pointers can coerce to single item pointers pointing to an array of length 1. Interesting. Single item mutable pointers can coerce to single item pointers pointing to an array of length 1. So we have a single value and we have a pointer to a single array. Oh, I see what they are saying here. So if you have just a value and then you have a pointer to an array with 1, you can point to, okay. Oh, okay. Great. Payload types and null coerce to optionals. Payload types. Num is a U8 equals 5. Maybe num is a question mark. Yeah, okay, yeah. So if you couldn't do this, then optionals would be horrible to work with. How would you assign to it? Like you would have to sort of dereference it or have another field on it, or I don't know really. But this is the same with union types, error union types. You can assign it to either the payload type or the special type. Payload types and errors coerce to error unions. Yeah. My error, yes, car. If you have an error union, you can set it to char or an error. Yes, undefined coerces to any type, or it would work. Okay. I mean, okay. I guess as some of these facts are like, okay, well, does it really matter? Like, I mean, it's like, what do I do with this information? It's like, it's sometimes when I read like math proofs, I'm not usually doing that, but it feels like that they're saying things that seem obvious, and why would you even need to state this, you know? But I realize that there is like a formality to it, and if you just scale away everything that you know and you only have the thing that you see in the paper, then it makes sense. But sometimes it's just like A equals A. Yeah. Yes. I don't know. I know there's like some kind of logic reason behind it, but yeah. Compiler type numbers correspond to compiler types. Yeah. Except like compile time ints, annoyingly, if you define a variable to be a comp time int like this, const a equals 5, and then later on you have an f32 is a divided by 2. Now it's gonna complain, because it's like, it says that this is an integer, so this is gonna truncate and be like 2. So you have to do this to make it work, which is very annoying because it just feels unnecessary. A equals A is a law of identity, is an axiom. Yeah. I get it. It's just that I don't know. So what I mean is, like, I don't know, to me personally, like, I understand why it's there and everything, but I just get the feeling when I read it, it's like, why would you even need to state this? It's like, it feels like you can derive this from something. I don't know. Maybe you can't. It's like the saying, like, okay, well, you have a set with A in it. Okay. There's no other elements in the set. Okay, but you didn't need to state that. Okay, now I'm just making things up, but usually, like, statements like that. Yeah, it's an axiom, which means it cannot be derived. Yeah. I don't know. It feels like you can derive it from. When the feeling I got was like, yeah, you could derive it from, like, common sense, but I know it's supposed to be a formal, logical definition, so it has to be sort of everything that it ever could. Like, yeah, you have to, like, scale away all of your knowledge or preconceived, I guess, things in order to, like, interpret it correctly. Tagged unions can coerce to the current tagged enum. Yes, very, very good. Enum coerce to a tagged union when the tagged field is a zero length type. Yes, I think I knew about that. 0-bit types like void can be coerced into single item pointers. What? Man, I wish they showed an example here. Is it like a void pointer? This doesn't make sense to me. 0-bit types like void can be coerced into single item pointers. You're turning something that is a void into something that is not. Why only single item pointers? Okay, I don't know. I would assume it coerces to a null pointer. Yeah, I wish they would show an example here because I don't understand. Okay, the last three are fairly esoteric, but you're more than welcome to read more about the official Zig language documentation and write your own experiments. So it's like if you have this guy here, and then you have an A, which is a U8. Well, this has to be a bar, I guess, and then 5, and then you can set this to that. Hang on. I think this needs to be a const. No, it's not, because this is immutable. Wait, and then we wait. This is a null, optional, pointer 0, like this. But I mean, this is weird. What is happening here? It doesn't have any. It doesn't have any runtime store. Like, it's not stored in runtime, this thing. So what's the purpose here? Well, I mean, I guess I have to read the documentation for that, but that's kind of weird. Okay, I'll write this down. Void can be coerced to single item pointers in blocks. Oh yeah. Oops. No, come on. Okay. Wait, that was wrong. Expected type, question mark, must coerce, use coercion rules 4 and 5. When it's right, this will work. This is, okay, so this is that. Do I need to do this? No, that seems weird. You did it backwards. You coerced. Oh, but it worked. That's what I was thinking. Like, what the hell is... Okay, so you mean like this, and if you have a void... No, wait. Yeah. And then you have a void. This is something. And then this is that. No, but it says 0-bit types can be coerced into single item pointers. So aren't you coercing a void value into a single item pointer? Oh yeah, sorry, I'm confused. This is and that's what we're doing here, right? So we're coercing, because we're taking the value of A, so we're coercing the value of this into this here, which is also weird, right? Why? What? How? No, wait. Let's set this to like undefined or something. Expected found const void. Maybe, okay, well, let's make this constant. Expected type thing found that pointer type child void cannot cast into pointer type. Pointer type child void cannot cast into pointer type child U8. No, okay, so it's not a pointer, it's just this. Maybe. Because it did work the other way around. Can be coerced into single item pointers. Maybe it needs to be mutable. Local variables never mutable. Okay. Wait. Yeah, this is never mutated, but what if we did that? And maybe this. No. Okay, so void curly brackets, is that how you construct the value of type void? So yeah, this is how you construct the value of type void, which is like a 0-bit thing, so it's not actually produced in the runtime code. I mean, I can't get this to work. It worked the other way around, like void can be coerced into single item pointers. Void I thought I made it work, but I didn't, probably. Hey Polaris7, how's it going? Welcome. Okay, I don't know. I have to read up on the, maybe I'll find it now because we're kinda looking at it. I just need to readjust the window here. There we go. And zig docs void. Like, I've never used this except for like return types, so void can be used for instantiating generic types. For example, given a map key value, one can pass a void for the value type to make it into a set. Wow, okay. Already this is new information for me. That's actually true. Like, the key is also, yeah, it's like the key is also like optimized, indexed. Yeah, okay, that's true. So, okay, but yeah, because you can set these there, and then in runtime these things will never actually take up any space as well. Wow, you define a map and you get a set for free. That's cool. This is different from using a dummy value for hash map value, but using void as a type of value type of hash map. That does not the field, doesn't matter. takes up less space. Further, all the code is with storing loaded values deleted as seen above. Yes, very cool. Void is distinct from any opaque. Void has known size of 0 bytes, and opaque has unknown but known 0 size. Expression types void are the only ones whose value can be ignored. For example, ignoring a non-void expression is a compiler. Yeah, you're ignoring the return value here, which you can't do. However, if the expression has type void with no error, expression's results can be explicitly ignored by assigning them to underscore. Okay, that was it. Maybe it says something here. For sometimes size of a 0, void integers u0 and i0. That's funny. Arrays and vectors with length 0 or with an element type that is 0-bit type. What about slices with 0 length? I guess they could technically still have a pointer. Maybe. An enum with only one tag. Yeah. A struct with all fields being 0-bit types. A union with only one field, which is a 0-bit type. Okay. Well, a union with multiple 0-bit types is just an enum, right? But it's like a convenient way of maybe refactoring into more fields that have different types. These types can only have one possible value, thus requires 0 bits to represent code. Makes use of these types not included in the finally generated code. Yes, very good. Wait, these assembly instructions do not have any code associated with void. They will preserve function called prologue and epilogue. BP is... what was that now? I forgot. Stack pointer. Is that the frame? BP, I think that's a stack frame. Maybe. Yeah. And we return. Does it use like this? So this puts, I think this puts it in racks, and then return. Would that use racks? No, wait, no, that's not true. It knows somehow where to return. Okay, whatever. Yeah, stack frame. I thought I put the return address in the stack, like implicitly with the instruction, like the call instruction. Okay. Anyway, void. For example, given a map. No, wait. We already read this. Okay, so that didn't go through this. Illegal behavior. Course. Oh yeah, C pointers. I forgot about this. Push the RBP to the top so it restores the stack pointer. The stack state prior to return at the bottom. Yes, but I was thinking about like how does it know where to return to? Like it should, that address needs to be stored somewhere. I thought I knew that it was pushed like implicitly by the instructions call and return. It's gonna be put on the stack or something like that. So that was confusing it there. Or is it called enter? Enter and return. Yeah, I don't know. Anyway, Undefined can requires to any type. Float literals, squares, vector, squares. Wait. Okay, maybe I should search for void. No. Maybe not. Okay, you know what? I'm gonna leave this. We're just gonna... yeah. Okay, let's figure this out. It's on the stack. Yeah, that's what I thought. Ret will pop the return address of the stack. Yeah. Yeah. Okay, so my letter. So what are we? Okay, let's just see. 4 and 5. What's that? Yes. And that. Yes. So what's the issue here? We have optional first, and then the pointer. Does this need to be a pointer? It's well, okay. We're dereferencing and then accessing. No. So you can chorus to this. I'm pretty sure. Like this. No? Wasn't that... oh. A 1. Oh, so 1, so that works. Or not. Oh, it's a pointer, so okay. Pointer to 1, okay, yeah. That works, okay. Now we need... so pointer to 1, okay, and then optional, there we go. There we go. Okay, this is not a usual thing, so I don't really see that as super helpful. But anyway, remember using if-else statements as expressions like this. Yes, like a ternary except with different syntax. Zig also lets you use for and while use as expressions. Yeah. Like return for functions, you can return a value while loop rock with a break true. Yes, very nice. But what value is returned from a loop if a break statement is never reached? We need a default expression. Thankfully, Zig loops have also the else clauses. As you might have guessed, these else clauses is evaluated when 1, a while loop condition becomes false, or 2, a for loop runs out of items. And yeah, and crucially it doesn't break out. So while true, break 2, else 0. Right, so we're breaking 2 immediately, so that's 2. 4, okay, 1 array f, break 3, yeah, that's the same thing. So I was learning Zig, how to take console input standard sum. Okay, well I can show you that. Let me, I can go here and this. Oh, you found it? Well, if you have any issues, you can just I can show you how to work with that a little bit. It can be a little bit complicated at first. I mean, there's a million ways to do it as well, so. 2, 3. Yes, if you do not provide an else clause, an empty one will be provided for you, which will evaluate to the void type, which is probably not what we want. So consider the else clause is essential when using loops as expressions. I mean, yeah, if you're trying to produce a value, you're just gonna make, you know, the compiler will tell you. But otherwise, I don't see it as essential. Oh yeah, if you're using them as expressions, okay, yeah, I guess. With that in mind, see if you can find or fix the problem with this problem. Unless you're guaranteed to break in here. Right? This will not, I mean, else, this will be else unreachable at this point. Right? Okay, anyway. Let's see here. Let's find the first language with 3-letter name term for the loop for loop. Okay. We've got a slice, but then we got a string, optional string, and we're looking through all the languages, program languages. And if the length is 3, we want to have it. So zig is perfect. And we are looking, if we have one, then yeah, okay, so we just add else null. There we go. Great, so now we're on 63. And I really do like the else, like the loop else. It's a very nice way, because otherwise you have to sort of have a variable that you, like a flag that you turn on if you were successful, and then you have to look at the flag instead of just having the else block. So I think that's a really nice thing. Okay, loop bodies are blocks, which are also expressions. We've seen how they can be used to evaluate return values. To further expand on this concept, it turns out we can also give names to blocks by applying a label. Yeah, my label. Once you have a block label, you can use break to exit from that block. Outer block, while true, break outer block. Yeah, it is. I'm not using it too much, but it's nice. If you have nested loops, you sometimes have to have this. It's also sometimes it's nice for documentation, sort of, as well, to just see what the hell is happening here. Like you can, I mean, potentially do this instead of naming a function for the same thing. But I mean, you probably want to have a function, but that will create. I guess it depends on how optimized you want the code to be. Although you can use inline functions, but I think inline functions are never guaranteed to actually be inline, so it's kind of weird. But okay, as we've just learned, you can return a value using a break statement. Does that mean you can return a value from any labeled block? Yes, it does. Const foo make 5. 5 equals to this break make 5. Yeah, so this is like, this is a code block where you can break to it's I mean, it's kind of like a little function. I'm pretty sure it has closure as well, like you can have it refer to things in the scope outside. I'm pretty sure. Labels can also be used with loops. Being able to break out of nested loops at a specific level is one of the things that you won't use every day, but when the time comes, it's incredibly convenient. Being able to return a value from an inner loop is sometimes so handy, it almost feels like cheating, and can help you avoid creating a lot of temporary variables. So we have 2 loops. While true, break 2 loop 2 else 0. Right. In the above example, the break exits from the outer loop labeled to loop and returns the value 2. The else clause is attached to the outer loop, the outer 2 loop, and would be evaluated if the loop somehow ended without the break having been cancelled. Finally, you can also block labels with the continue statement. Yes. As mentioned before, we'll soon understand why these two numbers don't need explicit types. Hang in there. They're both comp time ints. So they have that implicit type, which can be coerced into many different things. Okay, we got some food things. Okay, seems to be correct. Welcome to Cafeteria USA. Choose your favorite ingredients and we'll produce a delicious meal. Cafeteria customer note: not all ingredient combinations make a meal. The default meal is macaroni and cheese. Man, I'm getting hungry. Software developer note: hard coding ingredient numbers based on array position will be fine for a tiny example, but it would be downright criminal in a real application. Well, I guess you'll find out if you tried that. Okay, chill and cheese. Look at each food on the menu. We got a food loop. Now look at each ingredient required for the food. Required ingredient, required. Okay, so this is like the index. Required if it's required or not. If it's not required, we'll skip it. Okay. See if the customer wants this ingredient. Remember that it will will be the index number of the ingredient based on the position in the required ingredient list for each fold. Wanted ingredients if you want it. Okay, so we'll just have to check if the index is in there, and then it's true, otherwise it's false. Yeah, very nice use of this thing. Loop with an else and as an expression. We did not find this required ingredient, so we can't make this food continue the outer loop. Right. If we get this far, the required ingredients were all wanted for this food. Please return this food from the loop. What? But we're just breaking. Which is it? It's just the food, right? Break food. Yeah. And then we need else mac and cheese. So that would be the first one. Menu 0. Wait, what the hell? Ah, 0. Now, do you want to be? No, you're just a copy. Oops, we forgot to return default. Yes, challenge. You can also do away with the found variable in the inner loop. See if you can figure out how to do that. Okay, the found thing. Yeah, I mean, we could just do this. We loop through, and if it's true, what we're doing here is is it only one breakthrough? So this is true, so we should continue here. Otherwise we will continue food loop, the outer one. we can get rid of that. I'm pretty sure. No? Cheesy chili mac and cheese. Okay. So we're finding if they want the required ingredient, right? If they want it, that means we need to check the rest as well, right? So we're continuing. But if they didn't want the ingredient, we need to find another food. So we look for the next one, and if we're down here, that means that we found everything, and we can break with the food, otherwise we choose mac and cheese. I mean, will this work, or will this also not work? Oh, it did work. Okay, so there was something wrong with my implementation here. What if this is true, that means we basically continue, because that's the last thing we're doing, right? And if it's false, we continue. Like, I don't understand what the difference was. Okay. Yeah, this should be the same as... No, okay. Okay, so I continued inside of this for loop, which I should really just break instead. Yeah, it should be break and then here continue. Yeah, because I continued in here, that means I continue in this one and not the outside one. Okay, now this should be equivalent. But here we now we're at, like, in the outside scope. We're not in this for loop anymore. So we're supplying the label where we want to continue. Yeah. Okay, well, anyway, 64 built-ins. The Zig compiler provides built-in functions. You've already gone to use seeing and import. Yes, intcast, in from enum. Yeah, there's a whole bunch of weird ones of these. Built-ins are special because they are intrinsic to the Zig language itself, as opposed to being provided with a standard library. They are also special because they can provide functionality that is only possible with help from the compiler, such as introspection, the ability to examine type properties from within a program. Yes. But I mean, yeah. I guess those kinds of things could be exposed to, like, language constructs that could make it possible to maybe write functions that do the same thing as well. But I don't know. It's a very, like, convenient, magical way to do things. I don't mind it. Zig contains over 100 built-in functions. We're certainly not going to cover them all, but we can look at some interesting ones. Wow, are there so many? Before we begin, know that many built-in functions have parameters marked as comp time. It's probably fairly clear what we mean when we say that these parameters need to be known at compile time, but rest assured we'll be doing comp time subject real justice soon. Okay, so we've got print The second built-in alphabetically is add. Is that true? I don't get this. Is this? I mean, this isn't sorted here. I guess this is the first one. Adder space cast. I mean, yeah. There's a whole like I've never seen all of them. So add with overflow. A and B are numbers of any type. There's turn value is a tuple with a result and a possible overflow bit. Let's try it with a tiny 4-bit integer size to make it clear. So we're adding these. They should overflow. This would be like first these ones. And then these two should be that, and then that is overflow. Overflow. Okay. And so we get like, okay, it doesn't know what type this is. This is unfortunate. Well, this knows the type. What the hell? How? What? Okay, that's very strange. Check out our fancy formatting. B. Well, it means zero padded, align right with 4 width, print as a binary number, 0 pad, right align 4 digits. Yeah. Oh yeah, B for binary. Binary. Yeah, binary. The print below produce this and this and that. Okay. Sure. Let's make sense of this answer. If the value of b's in decimals, the value of b's in decimal is 5. Yes, this one. 4 plus 1 is 5. Let's add 5 to A. Let's go 1. See where it overflows. Yeah, so we sort of did this. Wait, what's going on here? Okay, it's just a so this is not like a, okay, this is kind of confusing. In the last 2 lines, the value of A is corrupted because there was an overflow, but the operations line 4 and 5 themselves do not overflow. There's a difference between a value that overflowed at some point now corrupted. A single operation that overflows and maybe causes subsequent errors. In practice, we usually notice the overflow value first and have to work our way backwards to the operation that caused the overflow. If there was no overflow at all while adding 5 to A, what value would my result hold? Write the answer into expected result. If there was no overflow, well, this is a U8. I mean, it's A plus 5. Or, yeah. Furthermore, here's a fun one. Bit reverse, integer, any type, integer is value to reverse. The return value will be the same type with the value bits reversed. Bit reverse. Now it's your turn. See if you can fix this attempt to use this built-in to reverse the bits of a U8 integer. Input U8 equals that tupni. So input reversed is bit reversed. Wait, what? Why? accepts any integer type or integer vector type. Reverses bit pattern. Why are we putting tupni in here? This only takes one argument. I guess that's the error. Oh, I see. This becomes an overflow. So I know how to fix it. I can cast this to a U8. But I guess if we check it, this is like 8, 12, 13. Yeah. Okay. 65. Zig is built in for mathematical operations such as square roots, sine, cosine, exponential, or yeah, the E thing, log, floor, but not ceiling, I don't think. But there are also like standard math equivalents of these, which is confusing. Sometimes, yeah, there's like slight differences. And lots of typecasting operations such as error, from int, float from int, pointer from int from pointer, int from enum. Spending part of the rainy days skimming through the complete list of built-ins in the official SIG documentation would be a bad use of your time. There are some seriously cool features in there. Check out call. Yeah, I think you can call like C functions with that, with like in a very specific way, or call functions in a a specific way. Compile log, embed file. Yeah, compile log we used a little bit. Embed file, you can load files in compile time and parse their data and do stuff in compile time with that. And source, which I've used for debugging purposes. I forgot now which one it is. No, it's like yeah, ztracy, traces, yeah. Okay. This learning resource is a bit suspicious. Those U4 seem like they're supposed to be unsigned, which means they cannot overflow. Oh, okay. Oh yeah. Well, I mean, yeah, that's true. Like because the CPU instructions doesn't have is it because it doesn't have an equivalent of, you know, you can't specify, yeah, this is a U4, so you have, so you're gonna, but isn't that that's so, okay, so that's what this is for then, I guess. I think what they're saying is that they're kind of emulating an overflow, you know, with this function. So you can put U4s in here and they were like, yeah, it's an overflow with this type, even though, you know, it's not a quote-unquote real overflow in the CPU. So they're kind of emulating the CPU here with this function, is what I'm taking from this. Good point. Because I was thinking that too. I was thinking, oh, so there you can get the CPU flag. If you want, because there are like there is a, like, you can say this or U4, you can do I think it's like percent plus or plus percent B. Now this is a special kind of plus. So usually Zig has safety. If you do this, that's gonna crash with overflow error in Zig. But if you do this, that's a special one which says that we are allowing wraparound operation here. So it's gonna wrap around. And then you can also do this. Wait, I think it's the other way around actually. This is the wraparound, and then this is like you know, it will have like the max, like if there was an overflow, it would have sort of the maximum value or minimum value depending on which way you're going. But you're not wrapping around, you're just stuck at the top or at the bottom. But you won't get a report like with this to say what happened. Makes sense, it's an overflow, but that's different from C. Yeah. So it's because like in Zig you can have these weird, you know, integers, and then they added this to kind of, I guess, mimic the overflow. Like I wouldn't know, like how could you get like like flags? I don't know. You would have to be able to, because you can write assembly here and get it that way if you want. To get the flags. Wait, where was I? Yeah, that one. We did that. Wait, we already. Oh yeah, now we're at 65. That's right. Spending budget. For now, we are going to complete our explanation of build-ins by exploring 3. Okay, so I know about this. That this type is nice. It's kind of hard to explain. I mean, if you're defining a struct that has a bunch of generic maybe parameters and everything, so it's kind of hard to maybe type out the whole type. You can use at this to as a shortcut to refer to the current type in the scope, basically. It's a nice thing if you have like generic types. Returns the innermost struct enum or union that function call is inside. Wait, returns the innermost struct enum or union that a function call is inside. A function call. Well, you can use it in the signature of a function. You don't have to have a function call. You can also use it in a declaration in the struct as well. Yeah, you don't have to be in a function call, I don't think, for that. Not all addition instructions modify the flags, such as LEA on x86. Right. Yeah. I don't know kind of what you're thinking, like if you have U4, that doesn't exist like as a type in the instruction set. They have, you know, you have like U8, U16, U32, U64, and there's gonna be overflow on those types, but not on U4. For those kind of like add whatever instruction is. But yeah, returns the innermost structure. Okay, returns information about any type in a data structure which will contain different information depending on which type you're examining. Yeah, type info is great if you're going to do any type of reflection in comp time. If you're writing a generic function, I use it for, I wrote a little library for iterators that can be generic for any type to iterate to, well, the element that you get when you iterate. 3 type returns type common to all input parameters. Each of which may be an expression. The type is resolved using the same peer type resolution process that the compiler itself uses when inferring types. Notice how the 2 functions which return types start with uppercase letters. This is a standard naming practice in Zig. Oh, I see. Is that why it's like that? Okay, I always wondered why this is like lowercase, this is large case. So, okay, that makes sense, sort of. This is like a type. It returns a type, so it's always, yeah, that's a convention in Zig. Like everything that is a type should be start at uppercase letter. Everything that's not a type should start with lowercase letters. Except if you, I mean, you don't have to follow. It's just a convention. But I mean, you can do this like max. You know, there's nothing preventing you from doing this. It's just that probably this would be the convention instead. I don't know. I've seen like mixed things. Okay. Me, myself, and Echo. Narcissus. Fetch the most beautiful type. Okay. Yeah, so here's an example of using this. So this would refer to this struct here, which is named Narcissus. And we're making a new Narcissus here. We cannot leave the me and myself fields undefined. Please set them here. Okay. Okay, so this is a pointer to itself. And this is the same. This determines a peer type from 3 separate references. They just happen to be all the same object. Yes. Okay. Wait. What the hell? I didn't know you could put multiple things in here. What? Type of is a special built-in function that takes any non-zero number of expressions as parameters, returns the type of the result using peer type resolution. I had no idea about this. I didn't know you could put multiple things in here. Why does it end here? The expressions are evaluated, however they are guaranteed to have no runtime side effects. I mean, yeah, it's comp time, so okay, this is weird. Where? Okay, there's documentation for that, which was not found. Okay, here we go. I'm interested in this. Oops. Peer type resolution. Oops. Peer type resolution occurs in this place. Switch if while for. How is this like making a, like, it's so almost like a union. It can be either type. Multiple break statements in a block, some binary. But I'm not sure if you can actually set a value or like define a variable to this type. This kind of type resolution chooses a type that all peer types can coerce into. Oh. Okay, then it's different from what I was thinking. Peer result int widening. Oh, I see. Okay, so C becomes a peer resolution here, which becomes an I16, I guess. Okay. Peer resolve arrays of different sizes to const slice. Okay. Expect memory equals true to be true. Bool to string. Oh. I was like, how did I do this? But that is just, you know, a function here. Okay. Expect comp time arrays different size const slice. Yeah, this is a const slice. Well, it's like a comp yeah. I think all these become this type. Pretty sure. All these constant strings become this type. Right? Or is it an array? No, I'm not sure actually. Okay, I guess it says that it's resolving array to a different size to const slice. So this is a const slice, so this should be the array, right? Yeah, I guess a slice can always stem from the array. Makes sense. Okay, well, great. Cool. So it's kind of okay. Well, this is all the same thing. So, okay, yeah, and I guess they were saying here the expressions are valid how they are guaranteed to have no runtime side effect. So basically, anything in here, like even if you're like dereferencing thing here, maybe you're calling a function, it won't actually get executed. It's only statically analyzed to get whatever type is gonna be the result. Oh dear, we seem to have done something wrong when calling this function. We called it as a method which would work if it had a self parameter, but it hasn't. See about. The fix for this is very subtle, but it makes a big difference. Yeah, so this should have a self, and it returns a type. Okay, so it doesn't need to be mutable. Yeah, so also this should be capital because it's a type. Okay, now we print a pithy statement about narcissus. Maximum narcissism. Okay, loves all things. His final words as was looking in those orders as they habitually watched were these: alas, my beloved boy, in vain. The place gave every word back in reply. He cried farewell, and echo cried farewell. Ovid, the metamorphoses translated by Angel. Okay. He has room in his heart for these things, right? Now, okay, this is a bit of comp time stuff. So we are grabbing the fields out of the reflection here of Narcissus. So here we get a comp time known list of fields, which has like the names of the field, the type, default value, yeah, these things here. So very nice, very cool. Please complete this if statement so that the field name will not be printed if the field is of type void, which is a 0-bit type that takes up no space at all. Yeah, so this is type. Alright. So if it's not equal to void, then we print it. Why are we not looping here? That's the whole point of these. Okay, Yuck, look at all the repeated code above. I don't know about you, but it makes me itchy. Alas, we cannot use the regular folder up here because fields can only be evaluated at compile time. Seems we'll be overdue to learn about this comp time stuff, doesn't it? Don't worry, we'll get there. Okay, well, I know how to do it. There is a way. And there's inline for... We're gonna go through it later, but I'm itching here for this. They cannot keep me waiting here. There we go. There you go. That fixed it for you. So inline 4, well, they're gonna go through it, so I won't go through it now. But it's now it works. Unused. Okay, well, can we have self be unused? Probably not. Let's just return type of self to fix that. Okay. Okay, what's going on down here? No, this exercise did not originally include the function below, but I changed that to zig 0.10. Well, I've never been there. I started at 0.13. Added the source file name to the type. Narcissus became built-ins 2.narcissus. Source file to the type. Source file name to the type. Oh, I see. To fix this, we've added this function. To strip the file name from the front of the type name, it returns a slice of the type name starting at the index +1 of character. Dot. We'll be seeing type name again in exercise 070. For now, you can see that it takes a type and returns a UH string. Okay, so we'll get from index of dot. We know that it has it. We'll add 1 and take the rest. Skip the dot there, yes. You can see that it takes a type. Yeah. Okay, we got some problems. Unable to resolve comp time value. 73. Oh, I see. So basically, yeah, so we're taking... Okay. I mean... This should be comp time known here. This should really be comp time known. I wonder if you can wrap it in a comp time... like this. No, because this should be comp time. This is a type of self, so we know the type. This should be known. Wait, it says unable to resolve comp time value. Okay, I think I know what they wanted us to do. Like we shouldn't do this or this. So let's go back. I think they wanted us to do this. So now we're calling it as like a static function. Yeah. Okay. I thought I could make it work there, but maybe not. Alright, 66. Compile time is a program. So this is where I think I could maybe they could teach me a lot of stuff here. It's a program environment while it is being compiled. In contrast, runtime is the environment while the compiled program is executing. Traditionally as machine code on a hardware CPU. Errors make an easy example. Compile time error caught by the compiler, usually resulting in a message to the programmer. Hopefully, runtime error either caught by the running program itself or by the host hardware or operating system. Could be gracefully caught and handled, or could cause the computer to crash or halt to catch fire. Oh my god. All compiled languages must perform a certain amount of logic at compile time in order to analyze the code, maintain a table of symbols, such as variable function names, etc. Optimizing compilers, well, all sane compiled languages, I guess you could say. Optimizing compilers can also figure out how much of a program can be pre-computed or inlined at the compile time to make the program resulting more. Optimizing compilers can also figure out how much of a program can be pre-computed or inline at compile time to make the resulting program more efficient. Yeah, that's the hard part about compilers. I think smart compilers can even unroll loops, turning their logic into a fast linear sequence of statements, at the usually very slight expense of the increased size of the repeated code. Yeah. So you're paying a little bit of memory in the program, or yeah, program size to get more, or spend, yeah, and then spend less CPU to do it. Or speed, I guess. Yeah, you get speed from it. Zig takes these concepts further by making these optimizations an integral part of the language itself. Okay. All numeric literals in Zig are of type comtime int or comtime float. They are arbitrary size, as big or as little as you need. Notice how we don't have to specify size like U8, I32, or F64 when you assign identifiers immutably with const. Yeah, we don't have to, but we can if we want. When we use these identifiers in our program, the values are inserted at compile time into the executable code. The identifiers const int and const float doesn't exist in our compiled application. Yeah, very good. Because they don't need to be put anywhere, they can just be substituted whenever they are used. Print, immutable, yeah. But something changes when we assign the exact same values to identifiers immutably with var. The literals are still comtime in the comtime float, but we wish to assign them identifiers which are mutable at runtime. To be mutable at runtime, these identifiers must refer to areas of memory. In order to refer to areas of memory, Zig must know exactly how much memory to reserve for these values. Therefore, it follows that we just specify numeric types with specific sizes. The comtime numbers will be coerced if they fit into your chosen runtime types. For this, it is necessary to specify a type, size, e.g. 32-bit. Okay, so this should be this, and this should be that. We can change what is stored at the areas set aside for var int, var float in the running compile program. Yes, bonus. Now that we're familiar with Zig's built-ins, we can also inspect the types to see what they are. No guessing needed. Yeah, and you can also use compile log as well. You could, instead of doing this to actually need to run the program, you can do compile log, and then if you need, you know, this is like a print here, so you have to do, or you can do format. Oh, we don't have standard. Okay. So format compile print, comtime print, and then we copy this and this. Yeah, and now we get the same log but in compile time, so we can run this to get oh, it doesn't show it now. There we show here. we're getting the output when we compile instead of having to run the program if you just want to do some introspection like that. So here we get the output there. Well, this is the output. This is the actual output here. Yeah. Yeah. Okay. It's a bit different. It looks a bit weird when you do compile log, but yeah. And when you do a compile log, if the compiler sees a compile log, it will not succeed the compilation automatically. So you have to kind of delete all these to make it work. But that's cool. Okay. Now, did I solve this? Yes. Okay. Now we're on 67. Will we actually complete this today? I don't know. I don't think so. Man, there was much more here than I thought. But now we're getting into areas where I might learn more. Finally. I mean, I think it's nice to do this to get all the bases covered, as I said. But yeah, we've seen that Zig implicitly performs some evaluations of compile time, but sometimes you want to explicitly request compile time evaluation. For that, we have a new keyword. Oh my god, comp time with stars in the background. Nice. When placed before a variable declaration, comp time guarantees that every usage of that variable will be performed at compile time. Yes. As a simple example, compare these two statements. Var bar1 equals 5. Error. Wait, what's error about? Oh yeah, because we have to set the type. That's right. And then, okay, so we can do this with comp time, but we cannot really use it as a runtime value. I think there's like limitations on how you can use this, but the first one gives us an error because Zig assumes multiple identifiers will be used at runtime, and we have not assigned a runtime type. Trying to use a comp-time int if of undetermined size at runtime is a memory crime and you are under arrest. The second one is okay because we've told Zig that bar2 is a compile time variable. Zig will help us ensure this is true and let us know if we made a mistake. All right. Okay. Print. In this contrived example, we have decided to allocate some arrays using a variable count, but something is missing. Okay, you know what? We'll do it like this. I don't think we're gonna complete this today, but I will order some food, and when they have arrived, we will quit this stream. Because I am hungry, very, very hungry. Yes. One second here. This one, yes. All right. This control example, we decided to allocate some arrays using a variable count. Something's missing. Well, this is missing for one. So since this needs to be in a array, array size, this needs to be a U size here. And then that should be that. Built-in bonus, the compile log built-in. Okay, now they're going through this. It's like a print statement, only operates the compile time, treats compiler calls as errors. You want to use them temporarily to debug compile time logic. Try on commenting this line and playing on it. Okay, we already did that, so there we go. And wait, what was the issue here? count plus equals 1. Oh, this needs to be com time, right? So we're okay. So okay, I didn't realize what was happening here. This needs to be comp time here. This is kind of weird, like you're reusing the same thing. I mean, I guess there could be a use for this, but it's kind of weird. Okay, so basically now this is, at this point this is 0. We add 1. This is 1 now. So this becomes an array of size 1 with 1a. Now it's 2, so this becomes an array of 2. Like, it just feels a little bit unsafe, but I don't know. I mean, it's probably safe. There we go. And here we can see, like, first one is 1, second one, yeah. I guess it's cool. Okay, 68. How long can we go here before the food arrives? Okay, you can also put comp time before a function parameter to enforce that the argument passed to the function must be known as compile time will actually be used in function like this is entire time. Debug print comp time format. Yeah. So all print functions look like this. You have a comp time known string that has to be a literal string, or you know, it has to be comp time known. You can concatenate with as well, but I've never seen that. You have args, which you can, which is like, it's not comp time known, it's runtime, but it's like it can be any type, so you can put in, you know, it has to be a tuple type, but you can put in anything in the tuple with any length, and it will magically work, which is nice. And it's all built into the language, so you can define functions like this yourself and do nice things. Notice that the format string parameter format is marked, or FMT is marked as comp time. One of the neat benefits of this is that the format string can be checked for errors at compile time rather than crashing at runtime. Yes, that's very true. So if you provide a format that is badly formatted, then you will get yelled at in compile time, which is nice because you catch that error before you run the program. You're guaranteed to catch the error. The actual formatting is done by standard format, and it contains a complete format string parser that runs entirely at compile time, which is really cool. All right, this struct is the model of a model boat. We can transform it to any scale we would like. 1/2 is half the size, 1/32 is 32 times smaller than the real thing, and so forth. Cool. Okay, we got a schooner, and we've got some stuff, and we can scale. Okay, so we can. So we're doing like sane checks on what scale you're setting in. But the downside here is that you cannot put a runtime known only value here. Let's say you take an input from the terminal or something to put a scale here, but you can, I guess, yeah, you can sort of sanitize the input first and then put it here. So you can still have this function to do that. Anyway, we did something neat here. We've anticipated the possibility of accidentally attempting. So basically what I'm saying is you can turn a runtime value into a comp time value if you do a bunch of checks. I guess we'll get to that as well. Rather than having this result in a divide by error at runtime, we turn it as a compile error. This is probably the correct solution most of the time, but our model program is very casual, and we just wanted to do what I mean and keep working. Please change this so that it sets a 0 scale to 1 instead. I mean, sure. What the hell is happening here? Okay, we set the scale. Hull length is not equal. Oh, we're dividing. Okay. This looks kind of weird because of the font that I have. It makes like, I think it's meant to be used for Haskell, and this, I think this means like not equal, which is kind of weird. I'm pretty sure at least. But this is like divide equal, so we're dividing this by my scale and assigning it a new value. All right. Are we done? Oh wait, okay. There we go. No. Wait, oh, I didn't go further down. Okay. Let's see. So we have 3 things here. Hey, we can't just pass this runtime value as an argument to scare me, but what would it let us do that? We could make it into a comp time. Whoops. And we don't then, well, yeah, we can specify it into U32. Okay. Yes. Oops, but don't fix this. Yeah, because we fixed it. Okay, what would happen if you did attempt to build a model scale of 1, 0? You're already done. Interesting. Or you would suffer a mental divide by 0 error. Well, probably first. C, you would construct a singularity and destroy the planet. I don't think so. But because the mass would be 0, so it's the same as okay, this is getting into physics a little bit maybe, because if you have like 0 mass, like even out in the universe, like the fields that permeates the universe, there's something going on, like there's some kind of thing. But they say like if you have I don't know, I feel like my intuition of it, there's a little bit of thickness to the fields, but if you thin it out, you would sort of destroy the fabric of space and time or something like that. I don't know. Anyway, I think it would be equivalent of just having yeah, just a boring option, this one. Unless you're okay, if you begin, let's say you have a magical spell, a magical ability to be able to shrink anything to any size. Okay, so now we're looking at shrinking. I mean, what does that even mean? You can't shrink an atom. Like, these particles are like a set size and stuff. Their properties don't really, I mean, yeah. So that's kind of weird in itself. Like, what does that even mean? But what I'm thinking is like, okay, well, let's just say you can shrink something, and I guess that would mean you're reducing the amount of atoms. Or you could just say you're shrinking everything down. But what would happen in the limit of that? Like, because you have to shrink it. Like, let's say you're halving it every second or something. You would have to do it. I guess you would have to like do it an infinite amount of time in order to shrink it down to 0. So what would happen in the limit of that? I don't know. Okay. How about a model in the scale of 0, 1? Oh. You're already done. I mean, I guess they're thinking like you take 0 times 1. You'd arrange nothing carefully into the form of original nothing but infinitely larger. You'd arrange nothing carefully into the form of original of the original nothing, but infinitely larger. But what would change though? It would still count as the same thing. It's just a I don't know. You would construct a singularity and destroy the block. Yeah, sure. Let's go with that. Answers can be found at the back of the... yeah. Alright. There we go. 69. One of the more common uses of CompTime function parameters is passing a type to a function. Yes, a generic function. In fact, types are only available at compile time, so the CompTime keyword is required here. So I always thought that this was kind of redundant. Like, if it's always required, why have it at all? Why not just say that it's always CompTime? Like, why implicitly CompTime? Please take a moment to put on wizard hat. I mean, maybe at some point you can have types in runtime. What would that give you though? Please take a moment to put on the wizard hat, which has been provided for you. We are about to use this ability to implement a generic function. Yes, sometimes when programming you do feel a little bit like a sorcerer or a wizard or something. Here we declare arrays of 3 different types and sizes at compile time from a function called neat. S1 equals make sequence, S2 equals make sequence, S3 equals make sequence, sequence of something 3 times. Okay. This function is pretty wild because it executes at runtime and is part of the final compiled program. I mean, just like almost any other function, the function is compiled with unchanging data sizes and types. Okay, and yet it also allows for different sizes and types. This seems paradoxical, but how could both things be true? Okay, so I thought that it would they created like separate functions that took each like a C++ templates that creates like copies of the function of the same function, but operating on different types. But here they say that they created one function. It's kind of like a union. Unchanging data sizes and types. Actually generates a okay, well here. Okay, here we go. To accomplish this, the Zig compiler actually generates a separate copy of the function for every okay, I guess they mean like in the code, like in separate function for every size type combination. So in this case, 3 different functions will be generated for you, each with machine code that handles the specific data size and type. Please fix this function so that the size parameter is guaranteed to be known at compile time. Sets the array of type T one second here. I think they are pretty soon here. It's going to be known at compile time. Sets the size of the array of type T, which is the sequence we're creating and returning. What is this? Size sequence. is... Wait, why is this... Oh, this needs to be comp time. And then this is size. Yeah. There we go. Alright, we're at 70. We made past 69. Okay, well, I don't think I'm gonna... They're here now, so I have to go and fetch the food. But yeah, that's gonna be it for this time. So thank you very much for watching and joining me here. And have a nice day, and I'll see you later. Bye-bye.